Hey there, really love with you, mate JJ. Today is new book teardown day. We're going to do a new book teardown. It's probably going to be a pretty long video. The old teardown videos tend to be pretty long. The book we'll be looking at is Electricity and Magnetism by Edward Purcell and David Morin. This particular edition is the third edition. It was published recently in the year 2013. It was updated by Morin, who inherited it from Purcell. Purcell, I believe, initially published this book in 1985. I don't know if that was the second edition or the first edition, I'm not sure. But this edition is the third edition, and that's the one we'll be looking at today. Oh, well, I think of it. Today's silly job title is Prime Hack. Today I'm the Prime Hack. The reason we're looking at electricity and magnetism is because it's referenced as the E&M textbook for learning the art of electronics, which I've been working on. The plan is to have the first lab out on Tuesday, so that should be coming up soon. Of course, I'm busy and I don't know if I'm going to make it, but I'm going to try. Yesterday I got a lot of work done. I got all of the notes in order. We're looking at 5 different books. The main book that we're doing, of course, is Learning the Art of Electronics, which is the lab course. We're going to be doing 1 lab every month for the next 2 years until that's all done. And of course, Learning the Art of Electronics is the course for the textbook, and the textbook is The Art of Electronics, which is, the magnum opus of electronics textbooks. So yes, what have we got here? This is the book I was just talking about. This is The Art of Electronics. And the lab course is also equally large. It's the second edition of Learning the Art of Electronics. I have written up notes for the X chapters, which is like supplementary material that comes from the people who made the Art of Electronics. It's stuff that wouldn't fit in the main volume. Of course, the book we'll be looking at today is this one, Electricity and Magnetism, which is basically the physics books that's referenced by the course. And there is another book floating around here somewhere that I'd like to show you. Where is it? Here it is. We did this recently, and of course this counts as an old book, and we've done the old book teardown for this like last week. This is the other book that gets referenced from Learning the Art of Electronics, and this is Principles of Electronic Circuits, second edition. So this is an old book. We've already done the old book teardown for this book. I think it ran for about 4 hours. It'll probably be about the same today to get through this one, maybe a bit quicker, I'm not sure. I'm going through this and making detailed notes of it as well. I'm only just beginning that process, though. I've only started in the first chapter, and that's not done yet. But I'm going to record this video today so it can come out on Saturday. I've got some other work to do for day job this weekend. But I do also have to get on with recording the first lab for Learning the Art of Electronics. So I'm a busy boy, but I'm gonna make time for this because I just like to do it. So that's what we're going to do together today. We're going to jump over the bench. I'm going to see what's inside this book. So let's do it. Well, here we are on the bench. Now, what have we got here? Some sort of power cable. All right, get that out of the way. I'm armed with a coffee. Very important. That's interesting. I've just got a little job to do. Let's do it together just quickly now. No, it's all right. We won't. We'll just get on with this. Now, on the back, so, yes, well, I suppose I should show you the front cover. This is Electricity and Magnetism, 3rd edition, from Edward M. Purcell and David J. Morin. On the back, we've got some people saying some nice things about us, published by Cambridge University Press. David Morin has brought Purcell's beautiful book up to date with a long prayed for gentle revision of this legendary work into everyday SI units, adding new material and citations to recent research. And if that were not enough, Morin, a connoisseur of problems, enriches this new edition with a bounty of challenging and fascinating exercises. This was from David Derby's University of Chicago Laboratory Schools. Then the next comment is from Peter Krieger, University of Toronto, who says, with the update to SI units and the addition of numerous worked examples and problems, this modernized version of Purcell's classic text should serve to re-establish for a new generation of students its well-deserved reputation as one of the finest and most popular undergraduate E&M texts ever written. Wow, high praise. And the third comment is from Daniel V. Schroeder from Weber State University, who says, Purcell's book taught a whole generation of physicists that you needn't travel at half the speed of light to see relativity in action. Magnetism is caused by length contraction. Fascinating. Radiation is a consequence of the cosmic speed limit. This welcome revision will bring these insights and many others to a new generation. Wow. There's 4 points here. The first, this classic textbook introduces students to the world of electricity and magnetism, covering all the standard introductory topics. This third edition is revised and updated by David Morin and now uses SI units. Students are supported by worked examples throughout the text and over 200 solved end-of-chapter problems. A further 350 homework exercises help develop and test students' understanding. Applications at the end of each chapter demonstrate how the concepts relate to the real world. A complete solutions manual for adopting instructors is available at cambridge.org/Purcell-Morin. I had a look at this, by the way, and I don't think I can get it because I'm not an educator. They apparently keep it pretty securely locked down, so yeah, it's not available to the riffraff like me. Now, there's an interesting cheat sheet here in the front of the book talking about things that I don't know very well at all. But it tells you here derived units. When it says derived units, it means things that can be expressed in the SI units, I guess, which aren't listed. I don't know why they didn't do that. Perhaps it's too simple for them. The derived units, the Newton, the joule, the ampere, the volt, the farad, the ohm, the watt, the Tesla. There was a really funny XKCD article that came out just today about the farad. I'll make sure I link you to it in the show notes. It's really hilarious. Okay, now fundamental constants. Okay, so we've got a bunch of things that are just constant. Speed of light, elementary charge, electron mass, proton mass, Avogadro's number, Boltzmann constant, Planck constant, gravitational constant, electron magnetic moment, proton magnetic moment, permittivity of free space, and permeability of free space. Also, that's interesting. The elementary charge is 4.8 ESU. So I don't know what the ESU is. I think it's the charge on an electron, but that number rings a bell. That says 4.8. I heard 4.7 when I was doing the revision of the Frank Hertz experiment, which was the first. It was the beginning of quantum mechanics, where they figured out that energy was quantized. Yeah, I think it was 1914 they did that experiment, and I remember just the number 4.7. So I think this is probably just it got improved the resolution of that number a bit over the years. I think they thought it was 4.7, but it's actually 4.8 by the looks of it. And here's Maxwell's equations, which are the basis of classical electromagnetism, which is the subject of this book. Apparently the various quantum theories and special relativity and this sort of thing didn't have a huge impact on this, and this was heavily verified with experiments as well. So as a theory, it holds water and it stood its ground over time, which is quite fascinating. So this theory is still current and useful. And here's some other theorems about surfaces and volumes and such that I don't understand. This book is actually a bit beyond my pay grade, to be candid. I don't understand it as well as I hope to one day. But we're not reading for understanding today. We're reading for breadth of exposure. We want to see all of the types of things that we might need to know about one day. We're not going to learn them all, of course, in this reading. We're just going to see that they exist. And it'll give us some material on which to hang our understanding as the days turn into months, turn into years, turn into knowledge. I will read you the front bit here though, and then we'll have a look at the table of contents. So, what do we got? Electricity and Magnetism. For 50 years, Edward M. Purcell's classic textbook has introduced students to the world of electricity and magnetism. This third edition has been brought up to date and is now in SI units. It features hundreds of new examples, problems and figures and contains discussions of real-life applications. The textbook covers all the standard introductory topics such as electrostatics, magnetism, circuits, electromagnetic waves, and electric and magnetic fields in matter. Taking a non-traditional approach, magnetism is derived as a relativistic effect. Mathematical concepts are introduced in parallel with the physical topics at hand, making the motivations clear. Macroscopic phenomena are derived rigorously from the underlying microscopic physics. With worked examples, hundreds of illustrations, and nearly 600 end-of-chapter problems and exercises, the book is ideal for electricity and magnetism courses. Solutions to the exercises are available for instructions at cambridge.org/Purcell Morin. Edward M. Purcell, 1912 to 1997, was the recipient of many rewards for his scientific, educational, and civic work. In 1952, he shared the Nobel Prize for Physics for the discovery of nuclear magnetic resonance in liquids and solids, an elegant and precise method of determining the chemical structure of materials that serves as the basis for numerous applications, including magnetic resonance imaging, MRI. During his career, he served as science advisor to President Dwight D. Eisenhower, John F. Kennedy, and Lyndon B. Johnson. David J. Morin is a lecturer and the Associate Director of Undergraduate Studies in the Department of Physics, Harvard University. He is the author of the textbook Introduction to Classical Mechanics, published by Cambridge University Press, 2008. Great, and off we go. So as I said earlier, this was first published, or previously published, in 1985. Oh, there we go. And the first there we go. Wow, so it was actually 1963 that this book came out. Fascinating. All right, here we go. There's a table of contents. And you know what? I've written up the table of contents for my notes, and that's already done. And I did flip through, and I noticed that the hierarchy in this book is really quite flat. Like in a lot of books, you'll have parts, and parts will have chapters, and chapters will have sections, and sections will have subsections. There are no parts in this book. It just goes straight into chapters. And then the levels don't get very deep. In the table of contents here, it's just 2 levels, chapters and sections, but there are actually subsections in some of the sections, I learned, and those sections aren't enumerated in the table of contents here, so we'll see them when we actually flip through. And there are a couple of prefaces here as well. And I'd like to read them. I think we will. And we'll read them in the chronological order. So we'll read them from the first edition to the second edition to the third edition. So we'll do them in reverse order that the printing has them in. Anyway, so we've got the 3 prefaces, as I said. Volume 2, I don't know why it calls it Volume 2. Presumably there was Volume 1. I don't know anything about it. If this is Volume 2, it's not clear anywhere on the front, so I really don't understand that. I don't get it. Okay, so let me tell you about the table of contents. Chapter 1, Electrostatics, Charges and Fields. Electric charge, conservation of charge, quantization of charge, Coulomb's law,
Energy of a system of charges. Electrical energy in a crystal lattice. The electric field. Charge distributions. Flux. Gauss's law. Field of a spherical charge distribution. Field of a line charge. Field of an infinite flat sheet of charge. The force on a layer of charge. Energy associated with the electric field. Applications. Now they do end every chapter with applications, which is interesting. I think when we flip through, we'll actually read the applications and we'll see if we can learn why physics is relevant, huh? We'll also be looking at the chapter summary. Every chapter has a chapter summary. So those are things we'll look at closely, the application and the chapter summary. Everything else we'll just flip past because we haven't got that much time. Chapter 2, the electric potential. Line integral of the electric field, potential difference and the potential function, gradient of a scalar function, derivation of the field from the potential, potential of a charge distribution, uniformly charged disk, dipoles, divergence of a vector function, Gauss's theorem and the differential form of Gauss's law, the divergence in Cartesian coordinates, the Laplacian, Laplace's equation, distinguishing the physics from the mathematics, the curl of a vector function, Stokes' theorem, the curl in Cartesian coordinates, the physical meaning of the curl, applications, chapter summary, problems, exercises. I won't continue to list those because they're in every chapter. Chapter 3, electric fields around conductors, conductors and insulators, conductors in the electrostatic field, the general electrostatic problem and the uniqueness theorem, image charges, capacitance and capacitors, potentials and charges on several conductors, energy stored in a capacitor, other views on the boundary value problem. Chapter 4, electric currents, electric current and current density, steady currents and charge conservation, electrical conductivity and Ohm's law, the physics of electrical conduction, conduction in metals, semiconductors, circuits and circuit elements, energy dissipation in current flow, electromotive force and the voltaic cell, networks with voltage sources, variable currents in capacitors and resistors. Chapter 5, the fields of moving charges. From Ørsted to Einstein. Sorry if I got that pronunciation wrong. Ørsted. I don't know how to pronounce it. Give me a sec, I'll look it up. Alright, so it's pronounced simply Ørsted. There you go, it's Ørsted. Where were we? Ørsted, where was he? Here. Alright, so we're doing chapter 5, the field of moving charges. From Ørsted to Einstein, magnetic forces, measurement of charge in motion, invariance of charge, electric field measured in different frames of reference, field of a point charge moving with constant velocity, field of a charge that starts or stops, force on a moving charge, interaction between a moving charge and other moving charges. Chapter 6, the magnetic field. Definition of the magnetic field. Some properties of the magnetic field. Vector potential. Field of any current carrying wire. Fields of rings and coils. Change in B at a current sheet. How the fields transform. Rowland's experiment. Electrical conduction in a magnetic field, the Hall effect. Chapter 7, electromagnetic induction. Faraday's discovery. Conducting rod moving through a uniform magnetic field. Loop moving through a non-uniform magnetic field. Stationary loop with the field source moving. Universal law of induction. Mutual inductance. A reciprocity theorem. Self-inductance. Circuit containing self-inductance. Energy stored in the magnetic field. Chapter 8, alternating current circuits. A resonant circuit. Alternating current. Complex exponential solutions. Alternating current networks. Admittance and impedance. Power and energy in alternating current circuits. Chapter 9, Maxwell's equations and electromagnetic waves. Something is missing. The displacement current. Maxwell's equations. An electromagnetic wave. Other waveforms, superposition of waves. Energy transport by electromagnetic waves. How a wave looks in a different frame. Chapter 10. Electric fields in matter. Dielectrics. The moments of a charge distribution. The potential and field of a dipole. The torque and the force on a dipole in an external field. Atomic and molecular dipoles induce dipole moments. Permanent dipole moments. The electric field caused by polarized matter. Another look at the capacitor. The field of a polarized sphere. An electric sphere in a uniform field. The field of a charge in a dielectric medium and Gauss's law. A microscopic view of the dielectric. Polarization in changing fields. The bound charge current. An electromagnetic wave in a dielectric. Chapter 11. Magnetic fields in matter. How various substances respond to a magnetic field. The absence of magnetic charge. The field of a current loop. The force on a dipole in an external field. Electric currents in atoms. Electron spin and magnetic moment. Magnetic susceptibility. The magnetic field caused by magnetized matter. The field of a permanent magnet. Free currents and the field H. Ferromagnetism. Chapter 12, Solutions to the Problems. Then it's chapters 1 to 11, Solutions to the Problems. The solutions to the exercises are not given. They're available in the book, but you can't buy the book unless you're an educator. If you are an educator and you can buy the book, let me know, because I'd love to get my hands on a copy of that book. And I won't be using it for cheating at my university studies, I promise. Then there are a bunch of appendices. So we've got Appendix A, differences between SI and Gaussian units. Appendix B is SI units of common quantities. Appendix C are unit conversions. Appendix D, SI and Gaussian formulas. Appendix E, exact relations among SI and Gaussian units. Appendix F, curvilinear coordinates. Appendix G, a short revision of special relativity. Appendix H, radiation by an accelerated charge. Appendix I, superconductivity. Appendix J, magnetic resonance. Appendix K, helpful formulas and facts. References and index. Cool. That's a really long list of appendices, and I'm interested in that. So if we've got enough time when we get to the end of the book, we might have a close look at the appendices. Let's see how we go. So we're going to read the prefaces in chronological order, which means we should start with the preface to Volume 2, Edition 1. Edition 1, this is the first edition. They're all Volume 2. I don't get that, as I said. All right. So, don't need a bookmark there for the moment. Let's just put the bookmark. Doesn't matter. So, preface to the first edition. The subject of this volume of the Berkeley Physics course is electricity and magnetism. The sequence of topics in rough outline is not unusual. Electrostatics, steady currents, magnetic fields, electromagnetic induction, electric and magnetic polarization in matter. However, our approach is different from the traditional one. The difference is most conspicuous in chapters 5 and 6, where, building on the work of Volume 1, we treat the electric and magnetic fields of moving charges as manifestations of relativity and the invariance of electric charge. This approach focuses attention on some fundamental questions, such as charge conservation, charge invariance, the meaning of field. The only formal apparatus of special relativity that is really necessary is the Lorentz transformation of coordinates and the velocity addition formula. It is essential, though, that the student bring to this part of the course some of the ideas and attitudes Volume 1 sought to develop, among them a readiness to look at things from different frames of reference, an appreciation of invariance, and a respect for symmetry arguments. We make much use also in Volume 2 of the arguments based on superposition. Give me a sec. I'm going to go and see what we're talking about with volume 1. See if I can figure that out. I'll be back. Okay, now I realized I've actually done this before. When I went over and plugged this all in, I found out that I'd already visited the links before, and I remember now. This book, by the way, is edition 3, but the older version is available for free on the internet. You can find a PDF copy at archive.org, and apparently it's legit. It had something to do with the funding was a federal grant or something, which meant that, I don't know, they had to release it. They were obliged to. So it's open source. You can get a copy, not of the 3rd edition, but of the old one if you're interested in it. Of course, it's all been redone in SI units, so you probably wouldn't want to mess around with the old one. It'll just confuse you. But if you're interested in old books, and I certainly am, you might like to get yourself a copy. Now, the reason they call it Volume 2 is because it was part of the Berkeley Physics course, which is a 5-volume physics course. The first volume is Mechanics. Then Volume 2, which is, of course, this book, is Electricity and Magnetism. Volume 3 is Waves. Volume 4 is Quantum Physics. And Volume 5 is Statistical Physics. And I have to say, of those 5 topics, after Electricity and Magnetism, I'd be interested most in statistical physics, then mechanics, then waves, and quantum physics last of all. Not because I'm not interested in quantum physics, just because I'm interested in those other things just a little bit more. Anyway, there we go. So on we go with the preface to the first edition. Our approach to electric and magnetic phenomena in matter is primarily microscopic, with emphasis on the nature of atomic and molecular dipoles, both electric and magnetic. Electric conduction also is described microscopically in the terms of a Drude-Lorentz model. Naturally, some questions have to be left open until the student takes up quantum physics in Volume 4. But we freely talk in a matter-of-fact way about molecules and atoms as electrical structures with size, shape, and stiffness, about electron orbits and spin. We try to treat carefully a question that is sometimes avoided and sometimes beclouded in introductory texts: the meaning of the macroscopic fields E and B inside a material. Fascinating. In volume, they're talking about in an atom, in the space between the electron shell and the nucleus. What do the electric and magnetic fields look like at those points of space where that are in that place? It'll be interesting to see what they have to say about that. I wouldn't even know where to begin. In Volume 2, the student's mathematical equipment is extended by adding some tools of the vector calculus: gradient, divergence, curl, and the Laplacian. These concepts are developed as needed in the early chapters. In its preliminary versions, Volume 2 has been used in several classes at the University of California. It has benefited from criticism, and many people connected with the Berkeley course, especially from contributions by E.D. Commons and F.S. Crawford Jr., who taught the first classes to use the text. They and their students discovered numerous places where clarification or something more drastic was needed. Many of the revisions were based on their suggestions. Students' criticism of the last preliminary version were collected by Robert Gorin, who also helped to organize the problems. Valuable criticism has come also from J.D. Govender, who used the preliminary version at the University of Texas, and from E.F. Taylor of Wesleyan University. Ideas were contributed by Alan Kaufman at an early stage of the writing. A. Felser worked through most of the first draft as our first test student. The development of this approach to electricity and magnetism was encouraged not only by our original course committee, but by colleagues active in a rather parallel development of new course material at the Massachusetts Institute of Technology. Among the latter, J.R. Tessman of the MIT Science Teaching Center and Tufts University was especially helpful and influential in the early formulation of the strategy. He has used the preliminary version in class at MIT, and his critical reading of the entire text has resulted in many further changes and corrections. Publication of the preliminary version with its successive revisions was supervised by Mrs. Mary R. Maloney. Mrs. Lila Lowell typed most of the manuscript. The illustrations were put into final form by Felix Cooper. The author of this volume remains deeply grateful to his friends in Berkeley, and most of all to Charles Kittel for the stimulation and constant encouragement that have made the long task enjoyable. Great. So that was the first preface, and this will be our second preface, also by Purcell, I imagine. And was it dated? No, it's a shame they didn't date his prefaces. Did you date the first one? No, that's a shame. Anyway, this is the preface to the second edition. This revision of Electricity and Magnetism, Volume 2 of the Berkeley Physics course, has been made with three broad aims in mind. First, I've tried to make the text clearer at many points. In years of use, teachers and students have found innumerable places where a simplification or reorganization of an explanation could make it easier to follow. Doubtless some opportunities for such improvements have still been missed, not too many, I hope. A second aim was to make the book practically independent of its companion volumes in the Berkeley Physics course. As originally conceived, it was bracketed between Volume 1, which provided the needed special relativity, and Volume 3, Waves and Oscillations, to which was allocated the topic of electromagnetic waves. As it turned out, Volume 2 has been rather widely used alone. In recognition of that, I have made certain changes and additions. A concise review of the relations of special relativity is included as Appendix A. Some previous introduction to relativity is still assumed. The review provides a handy reference and summary for the ideas and formulas we need to understand the fields of moving charges and their transformation from one frame to another. The development of Maxwell's equations for the vacuum has been transferred from the heavily loaded Chapter 7 on induction to a new Chapter 9, where it leads naturally into an elementary treatment of plane electromagnetic waves, both running and standing. The propagation of a wave in a dielectric medium can then be treated in Chapter 10 on electric fields in matter. A third need to modernize the treatment of certain topics was most urgent in the chapter on electrical conduction. A substantially rewritten Chapter 4 now includes a section on the physics of homogeneous semiconductors, including doped semiconductors. Devices are not included, not even a rectifying junction, but what is said about bands and donors and acceptors could serve as starting point for development of such topics by the instructor. Thanks to solid-state electronics, the physics of the voltaic cell has become even more relevant to daily life as the number of batteries in use approaches in order of magnitude the world's population. In the first edition of this book, I unwisely chose as the example of an electrolytic cell one cell, the Western Standard Cell, which advances in physics were soon to render utterly obsolete. The section has been replaced by an analysis with new diagrams of the lead-acid storage battery, ancient, ubiquitous, and far from obsolete. One would hardly have expected that, in the revision of an elementary text in classical electromagnetism, attention would have to be paid to new developments in particle physics. But that is the case for two questions that were discussed in the first edition: the significance of charge quantization and the apparent absence of magnetic monopoles. Observation of proton decay would profoundly affect our view of the first question. Assiduous readers assiduous searches for that, and also for magnetic monopoles, have at this writing yield no confirmed events, but the possibility of such fundamental discoveries remains open. 3 special topics, optional extension of the text, are introduced in short appendixes. Appendix B, radiation by an accelerated charge. Appendix C, superconductivity. And Appendix D, magnetic resonance. I'm not sure if those are still here. This is the second edition he's talking about. What was the first one? Radiation by accelerated charge. We got that. Radiation by accelerating. Yeah, there it is. Appendix H. And what about the other two? Superconductivity and magnetic resonance. So I think I remember seeing superconductivity. Yep, there it is. And magnetic. Okay, 1, 2, 3. They're all still there. Great. Our primary system of units remains the Gaussian CGS system. The SI units, ampere, coulomb, volt, ohm, and Tesla, are also introduced in the text and used in many of the problems. Major formulas are repeated in their SI formulation with explicit directions about units and conversion factors. The charts inside the back cover summarize the basic relations in both systems of units. A special chart in Chapter 11 reviews in both systems the relations involving magnetic polarization. The student is not expected or encouraged to memorize conversion factors, though some may be more or less familiar through use. But to look them up whenever needed. There is no objection to a mixed unit like the ohm centimeter, still often used for resistivity, providing its meaning is perfectly clear. The definition of the meter in terms of an assigned value for the speed of light, which has just become official, simplifies the exact relation among the units, as briefly explained in Appendix E. There are some 300 problems, more than half of them new. It is not possible to thank individually all the teachers and students who have made good suggestions for changes and corrections. I fear that some will be disappointed to find that their suggestions have not been followed quite as they intended. That the net result is a substantial improvement. I hope most readers familiar with the first edition will agree. Mistakes, both old and new, will surely be found. Communications pointing them out will be gratefully received. It is a pleasure to thank Olive S. Rand for her patient and skillful assistance in the production of the manuscript. And here is the preface to the third edition, which is presumably written by Morin and not Purcell. Well, of course, because Purcell died 20 years before it was published. Wow. 1997 they said he lived to. And this came out in, what did it say, 2013, was it? Seems very recent. But it must have been. Yeah, 2013. Wow. So it lay dormant for like nearly 20 years since the guy died. That's amazing. All right, this is the preface to the third volume, and once it's done, we can get on with some actual reading. For 50 years, physics students have enjoyed learning about electricity and magnetism through the first 2 editions of this book. The purpose of the present edition is to bring certain things up to date and to add new material in the hopes that the trend will continue. The main changes from the second edition are 1. The conversion from Gaussian units to SI units, and 2. The addition of many solved problems and examples. The first of these changes is due to the fact that the vast majority of courses on electricity and magnetism are now taught in SI units. The second edition fell out of print at one point, and it was hard to watch such a wonderful book fade away because it wasn't compatible with the way the subject is presently taught. Of course, there are differing opinions as to which system of units is better for an introductory course, but this issue is moot given the reality of these courses. For students interested in working with Gaussian units, or for instructors who want their students to gain exposure to both systems, I've created a number of appendices that should be helpful. Appendix A discusses the differences between the SI and Gaussian systems. Appendix C derives the conversion factors between the corresponding units in the 2 systems. Appendix D explains how to convert formulas using SI to Gaussian. It then lists side by side the SI and Gaussian expressions for every important result in the book. A little time spent looking at this appendix will make it clear how to convert formulas from one system to the other. The second main change in the book is the addition of many solved problems and also many new examples in the text. Each chapter ends with problems and exercises. The solutions to the problems are located in chapter 12. The only official difference between the problems and exercises is that the problems have solutions included, whereas the exercises do not. A separate solutions manual for the exercises is available to instructors. In practice, however, one difference is that some of the more theorem-ish results are presented in the problems so that students can use these results in other problems or exercises. Some advice on using the solutions to the problems. Problems and exercises are given a very subjective difficulty rating from 1 star to 5 stars. If you are having trouble solving a problem, it is critical that you don't look at the solution too soon. Brood over it for a while. If you do finally look at the solution, don't just read it through. Instead, cover it up with a piece of paper and read one line at a time until you reach a hint to get you started. Then set the book down, then set the book aside and work things out for real. That's the only way it will sink in. It's quite astonishing how unhelpful it is simply to read a solution. You'd think it would do some good, but in fact it is completely ineffective in raising your understanding to the next level. Of course, it's funny because in this book that's not our goal. We're just surveying the territory. We're not trying to learn so we can pass an exam. So we won't be engaging at that level, but we've only got a couple of hours, not a couple of semesters. Of course, a careful reading of the text, including perhaps a few problem solutions, is necessary to get the basics down. But if level 1 is understanding the basic concepts, level 2 is being able to apply those concepts, then you can read and read until the cows come home and you'll never get past level 1. The overall structure of the text is essentially the same as in the second edition, although a few new sections have been added. Section 2.7 introduces dipoles. The more formal treatment of dipoles, along with their applications, remains in place in Chapter 10. But because the fundamentals of dipoles can be understood using only the concepts developed in Chapters 1 and 2, it seems appropriate to cover the subject earlier in the book. Section 8.3 introduces the important technique of solving differential equations by forming complex solutions and then taking the real part. Section 962 deals with the Poynting vector, which opens up the door to some very cool problems. Each chapter concludes with a list of everyday applications of electricity and magnetism. The discussions are brief. The main purpose of these sections is to present a list of fun topics that deserve further investigation. You can carry onward with some combination of books, internet, people, pondering. There is effectively an infinite amount of information out there. See the references at the beginning of section 116 for some starting points. So my goal in these sections is simply to provide a springboard for further study. The intertwined nature of electricity, magnetism, and relativity is discussed in detail in Chapter 5. Many students find this material highly illuminating, although some find it a bit difficult. However, these groups are by no means mutually exclusive. For instructors who wish to take a less theoretical route, it is possible to skip directly from Chapter 4 to Chapter 6 with only a brief mention of the main result from Chapter 5, namely the magnetic field due to a straight current carrying wire. The use of non-Cartesian coordinates, cylindrical or spherical, is more prominent in the present edition. For setups possessing certain symmetries, a wisely chosen system of coordinates can greatly simplify the calculations. Appendix F gives a review of the various vector operators in the different systems. Compared with the second edition, the level of difficulty of the present edition is slightly higher due to a number of hefty problems that have been added. If you are looking for an extra challenge, these problems should keep you on your toes. However, if these are ignored, which they certainly can be in any standard course using this book, then the level of difficulty is roughly the same. I am grateful to all the students who used a draft version of this book and provided feedback. Their input has been invaluable. I would also like to thank Jacob Barandis for many illuminating discussions of the more subtle topics in the book. Paul Horowitz, oh, there we go, Paul Horowitz. There you go. He's the guy who wrote The Art of Electronics. Wow. Paul Horowitz helped to get the project off the ground and has been an endless supplier of cool facts. It was a pleasure brainstorming with Andrew Milowski, who offered many ideas for clever new problems. Howard Georgie and Wolfgang Ruckner provided much appreciated sounding boards and sanity checks. Takuya Kitagawa carefully read through a draft version and offered many helpful suggestions. I thank Ali Woolat and Irene Pizzi for their professional work in producing the layout of the book and copy editing the manuscript. Other friends and colleagues whose input I am grateful for are Lindsay Barnes, Simon Kaplan, Alan. There's a long list of names and I don't know how to pronounce them, so thank you to all those people. Despite careful editing, there is zero probability that this book is error-free. A great deal of new material has been added and errors have undoubtedly crept in. If anything looks amiss, please check the webpage at cambridge.org/Purcell Morin for a list of typos, updates, etc. And please let me know if you discover something that isn't already posted. Suggestions are always welcome. And that was from David Morin. All right, here we go. So we're just going to flip through. We're going to look at the applications. We're going to read the chapter summaries, which come at the end of the chapter. And then we're going to have a look at the appendixes, and then we're going to call it done. So we'll read the overview. We'll read the overview and the summary and the applications. All right. This is chapter 1, electrostatics, charges and fields. The existence of this book is owed both figuratively and literally to the fact that the building blocks of matter possess a quality called charge. Two important aspects of charge are conservation and quantization. The electric force between two charges is given by Coulomb's law. Like the gravitational force, the electric force falls off like 1 on r squared. It is conservative, so we can talk about the potential energy of a system of charges, the work done in assembling them. A very useful concept is the electric field, which is defined as the force per unit charge. Every point in space has a unique electric field associated with it. We can define the flux of the electric field through a given surface. This leads us to Gauss's law, which is an alternative way of stating Coulomb's law. In cases involving sufficient symmetry, it is much quicker to calculate the electric field via Gauss's law than via Coulomb's law and direct integration. Finally, we discuss the energy density in the electric field, which provides another way of calculating the potential energy of a system. Now we're off. Electric charge, conservation of charge, quantization of charge, Coulomb's law, energy of a system of charges, a little bit of calculus there, electrical energy in a crystal lattice, the electric field, there we go, some diagrams showing the electric field, charge distributions, flux, Gauss's law, field of a spherical charge distribution, field of a line charge, field of an infinite flat sheet of charge. That's another XKCD comic. That's 2 now. Let me see. What are we going to write? I need a pencil. Here's a pencil. So XKCD. I'm going to tell you about the Farad, and I'm going to tell you about nerd sniping. That's pretty funny. That's what this reminds me of. You'll get the joke when you see the cartoon, the comic. Field of an infinite flat sheet of charge. The force on a layer of charge. Energy associated with the electric field. Applications. Here we go. Each chapter of this book concludes with a list of everyday applications of the topics covered in the chapter. The discussions are brief. It would take many pages to explain each item in detail. Real-life physics tends to involve countless variations, complications, and subtleties. The main purpose here is just to say a few words to convince you that the applications are interesting and worthy of further study. You can carry onward with some combination of books, internet, people pondering. There is effectively an infinite amount of information out there, so you should take advantage of it. Two books packed full of real-life applications are The Flying Circuits of Physics, published 2007, and How Things Work, published 2010. And some very informative websites are, the Flying Circuits of Circuits of Physics has a website as well. How Stuff Works, there you go, that's got a mention. ExplainThatStuff.com, okay, and Wikipedia, of course. These websites can point you to more technical sources if you want to pursue things at a more advanced level. With the exception of the gravitational force keeping us on the Earth and ignoring magnets for the time being, essentially all everyday forces are electrostatic in origin, with some quantum mechanics mixed in to make things stable. See Earnshaw's theorem in section 212. Friction, tension, normal force, etc., all boil down to the electric forces between the electrons in the various atoms and molecules. You can open a door by pushing on it because the forces between neighboring molecules in the door and also in your hand are sufficiently strong. We can ignore the gravitational force between everyday sized objects because the gravitational force is so much weaker than the electric force. See problem 1.1. Only if one of the objects is the Earth does the gravitational force matter. And even in that case, it is quite remarkable that the electric forces between the molecules in, say, a wooden board that you might be standing on can completely balance the gravitational force on you due to the entire Earth. However, this wouldn't be the case if you attempt to stand on a lake, unless it's frozen. If you want to give an object a net charge, a possible way is via the triboelectric effect. If certain materials are rubbed against each other, they can become charged. For example, rubbing wool and Teflon together causes the wool to become positively charged and the Teflon negatively charged. The mechanism is simple. The Teflon simply grabs electrons from the wool. The determination of which material ends up with extra electrons depends on the electronic structure of the molecules in the materials. It turns out that actual rubbing isn't necessary. Simply touching and separating the materials can produce an imbalance of charge. Triboelectric effects are mitigated by humid air because the water molecules in the air are inclined to give or receive electrons depending on which of these actions neutralizes the object. This is due to the fact that water molecules are polar, that is, they are electrically lopsided. Polar molecules will be discussed in chapter 10. The electrical breakdown of air occurs when the electric field reaches a strength of about 3 times 10 to the 6 volts per meter. In fields this strong, electrons are ripped from molecules in the air. They are then accelerated by the field and collide with other molecules, knocking electrons out of these molecules and so on in a cascading process. The result is a spark, because eventually the electrons will combine in a more friendly manner with molecules and drop down to a lower energy level, emitting the light you see. If you shuffle your feet on a carpet and then bring your finger close to a grounded object, you will see a spark. The electric field near the surface of the Earth is about 100 volts per meter, pointing downward. You can show that this implies a charge of minus 5 times 10 to the 5 coulombs on the Earth. The atmosphere contains roughly the opposite charge, so that the Earth plus atmosphere system is essentially neutral, as it must be. Why? If there were no regenerative process, charge would leak between the ground and the atmosphere, and they would neutralize each other in about an hour. But there is a regenerative process. Lightning. This is a spectacular example of electrical breakdown. There are millions of lightning strikes per day over the surface of the Earth, the vast majority of which transfer negative charge to the Earth. A lightning strike is the result of the strong electric field that is produced by the buildup, or rather the separation, of charge in a cloud. This separation arises from the charge carried on moving raindrops, although the exact process is rather complicated. See the interesting discussion in Chapter 9 of Feynman et al. Alright, let's see if we can find that. Alright. Lightning can also arise from the charge carried on dust particles in coal mines, flour mills, grain storage facilities, etc. The result can be a deadly explosion. A more gentle form of electrical breakdown is corona discharge. Near the tip of a charged pointing object, such as a needle, the field is large but then falls off rapidly. You can model the needle roughly as having a tiny charged sphere on its end. Electrons are ripped off the needle, or off the air molecules, very close to the needle, but the field further away isn't large enough to sustain the breakdown. So there is a slow leakage instead of an abrupt spark. This leakage can sometimes be seen as a faint glow. Examples are St. Elmo's fire at the tips of ship masts and a glow at the tips of airplane wings. Electrostatic paint sprayers can produce very even coats of paint. As the paint leaves the sprayer, an electrode gives it a charge. This causes the drops in the paint mist to repel each other, helping to create a uniform mist with no clumping. If the object being painted is grounded, or given the opposite charge, the paint will be attracted to it, leading to less wasted paint, less mess, and less inhalation of paint mist. When painting a metal pipe, for example, the mist will wrap around and partially coat the back side, instead of just sailing off into the air. Photocopiers work by giving the toner powder a charge and giving certain locations on a drum or belt the opposite charge. These locations on the drum can be made to correspond to the location of ink on the original paper. This is accomplished by coating the drum with a photoconductive material, that is, one that becomes conductive when exposed to light. The entire surface of the drum is given an initial charge and then exposed to light at locations corresponding to the white areas on the original page, accomplished by reflecting light off the page. The charge can be made to flow off these newly conductive locations on the drum, leaving charge only at the location corresponding to the ink. When the oppositely charged toner is brought nearby, it is attracted to these locations on the drum. The toner is then transferred to a piece of paper, producing the desired copy. Electronic paper, used in many ebook readers, works by using electric fields to rotate or translate small black and white objects. One technique uses tiny spheres, about 10 to the minus 4 meters in diameter, that are black on one side and white on the other, with the sides being oppositely charged. Another technique uses similarly tiny spheres that are filled with many even tinier charged white particles along with a dark dye. In both cases, a narrow gap between sheets of electrodes, with one sheet being the transparent sheet that you look through, is filled with the spheres. By depositing a specific pattern of charge on the sheets, the color of the objects facing your eye can be controlled. In the first system, the black and white spheres rotate accordingly. In the second system, the tiny white particles pile up on one side of the sphere. In contrast with the standard LCD computer screen, electronic paper acts like normal paper in that it doesn't produce its own light. An outside light source is needed to view the page. An important advantage of electronic paper is that it uses a very small amount of power. A battery is needed only when the page is refreshed, whereas LCD screen requires continual refreshing. All right. Chapter summary. Electric charge, which can be positive or negative, is both conserved and quantized. The force between two charges is given by Coulomb's law, which is this monster here. Integrating this force, we find that the potential energy of a system of charges, which is the work necessary to bring them in from infinity, equals this monster here. Wow. The electric field, due to a charge distribution, is, depending on whether the distribution is continuous or discrete, either this or this. Okay, the force on a test charge Q due to the field is F equals QE. The flux of an electric field through a surface S is given as this. Gauss's law states that the flux of the electric field E through any closed surface equals 1 on epsilon 0 times the total charge enclosed by the surface. That is, depending on whether the distribution is continuous or discrete. Gauss's law gives the fields for a sphere, line, and sheet of charge as here. More generally, the discontinuity in the normal component of E across a sheet is delta E. I don't know how to pronounce that. Okay. Gauss's law is always valid, though it is useful for calculating the electric field only in cases where there is sufficient symmetry. The force per unit area on a layer of charge equals the density times the average of the fields on either side. The energy density of an electric field is epsilon 0 E squared on 2, so the total energy in a system equals this here. And then we've got our problems, and then we've got our exercises, and then we'll be on to chapter 2. I'm sorry I can't pronounce all of the Greek letters and everything, all the symbols in the mathematics. I would like to learn all of this stuff one day, but I won't be learning it all today. The electric potential, chapter 2. The first half of this chapter deals mainly with the potential associated with an electric field. The second half covers a number of mathematical topics that will be critical in our treatment of electromagnetism. The potential difference between 2 points is defined to be the negative line integral of the electric field. Equivalently, the electric field equals the negative gradient of the potential. Just as the electric field is the force per unit charge, the potential is the potential energy per unit charge. We give a number of examples involving the calculation of the potential due to a given charge distribution. One important example is the dipole, which consists of 2 equal and opposite charges. We will have much more to say about these applications of dipoles in chapter 10. Turning to mathematics, we introduce the divergence, which gives a measure of the flux of a vector field out of a small volume. We prove Gauss's theorem, or the divergence theorem, and then use it to write Gauss's law in differential form. The result is the first of the 4 equations known as Maxwell's equations, the subject of chapter 9. We explicitly calculate the divergence in Cartesian coordinates. The divergence of the gradient is known as the Laplacian operator. The divergence of the gradient is known as the Laplacian operator. Functions whose Laplacian equals 0 have many important properties, one of which leads to Earnshaw's theorem, which states that it is impossible to construct a stable electrostatic equilibrium in empty space. We introduce the curl, which gives a measure of the line integral of a vector field around a small closed curve. We prove Stokes' theorem and explicitly calculate the curl in Cartesian coordinates. The conservative nature of a static electric field implies that its curl is 0. See Appendix F for a discussion of the various vector operators in different coordinate systems. And then we're off on chapter 2. Line integral of the electric field, potential difference and the potential function, gradient of a scalar function, derivation of the field from the potential, potential of a charge distribution. uniformly charged disk. Calculation, is that phi? I think it's phi. Yeah, it's phi. That's phi. I don't know if it's capital phi or lower phi. Hard to say. I think it's lower phi. But my lower phi does actually look a bit different, so it might be a font thing, I'm not sure. Anyway, that's the calculation of phi and E. I think E is the electric field, but don't quote me. All right, the shapes of the curves, divergence of a vector function, Gauss's theorem and the differential form of Gauss's law, the divergence in Cartesian coordinates, Laplace's equation, distinguishing the physics from the mathematics. That's an interesting idea. In the preceding sections, we have been concerned with mathematical relations and new ways of expressing familiar facts. It may help to sort out physics from mathematics and law from definition if we try to imagine how things would be if the electric force were not a pure inverse square force, but instead a force with a finite range, for instance, a force varying like this. Then Gauss's law in the integral form expressed in equation 250 would surely fail, for by taking a very large surface enclosing some sources, we would find a vanishingly small field on its surface. The flux would go to zero as the surface expanded rather than remain constant. However, we could still define a field at every point in space. We could calculate the divergence of that field, and equation 251, which describes a mathematical property of any vector field, will still be true. Is there a contradiction here? No, because equation 252 would also fail. The divergence of the field would no longer be the same as the source density. We can understand this by noting that a small volume empty of sources could still have a net flux through it owing to the effect of a source outside the volume if the field has finite range. As suggested in figure 228, more flux would enter the side near the source than would leave the volume. Thus, we may say that equations 250 and 252 express the same physical law, the inverse square law that Coulomb established by direct measurement of the forces between charged bodies, while equation 251 is an expression of a mathematical theorem that enables us to translate our statement of this law from potential to integral form, or the reverse. The relations that connect E, I think that's rho and that's phi, are gathered together in figure 229a. The analogous expression in Gaussian units is shown in figure 229b. How can we justify these differential relations between source and field in a world where electric charge is really not a smooth jelly, but is concentrated on particles whose interior we know very little about? Actually, a statement like equation 272, Poisson's equation, is meaningful on a macroscopic scale only. The charge density rho is to be just check that is rho. Yeah, that's rho. The charge density rho is to be interpreted as an average over some small but finite region containing many particles. Thus, the function rho cannot be continuous in the way a mathematician might prefer. When we let our region VI shrink down in the course of demonstrating the differential form of Gauss's law, we know as physicists that we mustn't let it shrink too far. This is awkward perhaps, but the fact is that we make out very well with the continuum model in large-scale electrical systems. In the atomic world, we have the elementary particles and vacuum. Inside the particles, even if Coulomb's law turns out to have some kind of meaning, much else is going on. The vacuum, so far as electrostatics is concerned, is ruled by Laplace's equation. Still, we cannot be sure that, even in the vacuum, passage to a limit of zero size has physical meaning. Okay. The curl of a vector function. Stokes' theorem. It's this monster here. The curl in Cartesian coordinates. The physical meaning of the curl. Applications. As mentioned in section 116, the electrical breakdown of air occurs at a field of about 3 times 10 to the 6 volts per meter. So if you shuffle your feet on a carpet and then generate a spark with a grounded object, and if the spark is 1 millimeter long, then assuming that the field is roughly constant over this 1 millimeter distance, your potential was given by phi equals ED equals goes to phi equals 3 times 10 to the 6 volt per meter divided by 10 to the minus 3 meters equals 3,000 volts. Conversely, if you rub a balloon on your hair and it achieves a potential of 3,000 volts, and if the radius is 0.1 meters, which is 10 centimeters, then the charge on it is given by phi equals kq on r goes to q equals 3,000 times 0.1 divided by 9 times 10 to the power of 9 approximately equals 3 times 10 to the minus 8 coulombs, or about 100 ESU. I don't know how you pronounce ESU. Although 3000 volt might sound like a dangerous voltage, it is quite safe in this case because of one of the factors that determines the severity of a shock is the amount of charge involved, and there simply isn't enough charge residing on the balloon to cause much pain when it flows off. 3000 volts and an unlimited supply of charge would be a different story. Dear me, wouldn't it? However, the spark from an object like a balloon can be dangerous if it occurs in the presence of flammable gas, such as the gasoline vapors present at a gas station. If a voltage difference is somehow generated between different objects, a dangerous electrical breakdown can occur. One way of generating a voltage difference is to get back in your car while pumping the gas. Triboelectric effects between you and the car seat can produce charge transfer, causing you and the car to end up with different potentials, assuming that you don't touch any of its metal as you get back out. So don't get back in your car, or if you must, be sure to touch the grounded object far from the hose nozzle after you get out. There are also triboelectric effects from the gasoline moving through the hose. The relative motion between the fast-moving gasoline in the middle of the hose and the stationary bounded layer near the wall causes a transfer of electrons. The gasoline flowing into the tank is therefore charged. This is the reason why it is dangerous to fill a gas container that isn't grounded, for example one that is sitting in the bed of a pickup truck. A non-grounded container can achieve a significant potential. In the event there is an unlimited supply of charge, it isn't the particular voltage of a given object that makes things dangerous, but rather the voltage difference between the 2 points. In the end, it's the current that you need to worry about, but a large voltage difference means a larger current, all other things being equal. If you stand on a wooden stool with your hands on a small Van de Graaff generator held at 100 kilovolts, then you are also at this high potential, but there are no ill effects, assuming you don't mind your hair sticking up and barring pacemakers, etc. Because all parts of your body are at the same potential, there is no current flowing anywhere. Likewise, when flying birds take a break and sit on a power line, their potential is very high, but it is essentially the same throughout their bodies. The potential difference between their feet isn't large enough to push a noticeable current through their bodies. Also, of course, each bird is touching only one wire. This should be contrasted with the case of flying deer, whose bodies are large enough to touch two of the power lines, which have different potentials simultaneously. In the summer of 2011, a flying deer caused a power outage in a Montana town when it landed on power lines. Well, it was either a flying deer or a fawn dropped by an eagle. Fascinating. Okay, although the potential difference between a bird's feet on a wire is insignificant, the potential difference between your feet on the ground can be quite significant if there is a lightning strike nearby. The main difference between these two cases is that the resistivity, discussed in chapter 4, of the ground is much larger than that of the metal in a wire. The voltage difference between your feet can be thousands of volts, so current will travel up one leg and down the other, and there is more than enough charge in a lightning strike to do damage. So if there is a threat of lightning, then after taking all other precautions, you should stand with your feet close together. Livestock are at a bit of a disadvantage in this regard, since they don't stand that way. When the tires of a car roll along the ground, there is a turboelectric effect, so the car acquires a charge and hence also a voltage difference with the ground. When the car stops, this charge leaks off, but it takes a few seconds. This means that if there is no line at a toll booth, so that you encounter the toll collector right after stopping, and if you happen to touch their hand, you may receive and give a shock. Toll collectors are therefore probably happy to see at least a short line of cars. Helicopters can build up significant charge due to turboelectric effects between the blades in the air. The potential can reach 100 kilovolts. And because a helicopter is much larger than the balloon we discussed earlier, it can hold enough charge to generate a serious and perhaps lethal shock. If a cable is lowered from a hovering helicopter to a person being rescued, it is critical that the cable touch the ground or water before it touches the person, so that the discharge doesn't occur through the person. This is often accomplished by attaching to the bottom of a main cable a static discharge cable, which has a breakaway safety mechanism in case it gets snagged. The signals that travel along neurons take the form of modifications to the potential difference between the inside and outside of an axon, the long slender part of the neuron. A certain enzyme pumps Na plus sodium ions out of the axon and K plus potassium ions into it. But it pumps more of the former, so the exterior has a positive charge relative to the interior. This potential is about 70 millivolts higher. This is the resting potential. The nerve signal consists of a wave of depolarization where sodium ions rush into the axon and then potassium ions rush out. This modification to the potential is called the action potential. At a given location, it takes a few milliseconds for the signal to pass, and the potential then returns to its original value. The speed of the depolarization pulse along the neuron is roughly 100 meters per second. Although this nerve signal is in some sense an electrical signal, it isn't an actual current. There is no net flow of charge along the neuron. There is only the transverse motion of the sodium and potassium ions. The propagation of the signal depends on the opening and closing of various enzyme channels, so its speed isn't remotely close to the speed of an electrical signal in a metal wire, which is on the order of the speed of light. We got our chapter summary. For an electrostatic field, the line integral is independent of the path from P1 to P2. This allows us to define uniquely the electric potential difference as given. Relative to infinity, the potential due to a charge distribution is, depending on whether the distribution is continuous or discrete, as given in Cartesian coordinates, the gradient of a scalar function written as grad f, or I don't know how you pronounce the upside down delta, gradient of f. Okay, so the gradient of a scalar function is given by this monster. The gradient gives the direction in which f has the largest rate of increase. In terms of the gradient, the differential form of equation 299 is E equals the negative gradient of phi. This relation implies that the lines of the electric field are perpendicular to the surfaces of constant potential. The electrostatic potential energy difference is a charge Q between points P1, P2, and equals Q phi 21. Okay. The energy required to assemble a group of charges from infinity is, depending on whether the distribution is continuous or discrete, either this or this. Isn't that interesting? So you use integration for continuous and you use sum for discrete. Makes sense, I guess. The factor of 1/2 addresses the double counting of each pair of charges. All right. A dipole consists of two charges, plus or minus q, located at distance L apart. The dipole moment is P equals QL. At large distances, the potential and field due to a dipole are given as here. We verified that the electric field is everywhere perpendicular to the surfaces of constant potential. In Cartesian coordinates, the divergence of a vector function written as div f, or are they using that delta thing again? I really don't understand that. Okay, it's given as this. Looks very similar to the one we saw earlier. Doesn't it look like that? No. The divergence appears in Gauss's theorem, or the divergence theorem. Physically, the divergence equals the flux of F out of a volume divided by the volume in the limit where the volume becomes infinitesimal. Combining Gauss's theorem with Gauss's law gives this as this is the first of Maxwell's equations. In Cartesian coordinates, the Laplacian of a scalar function written as this or this or this is this. In terms of the Laplacian, equations 2102 and 2107 can be combined to give this. This is called Poisson's equation. It is the final link in figure 229, which shows all the relations among the electrostatic quantities. E, phi, rho. A special case of equation 2109 is Laplace's equation, which is this. If phi satisfies this equation, then the average value of phi over the surface of any sphere equals the value of phi at the center of the sphere. This fact, or alternatively Gauss's law, implies that it is impossible to construct an electrostatic field that will hold a charged particle in stable equilibrium in empty space. In Cartesian coordinates, the curl of a vector function is given as this. The curl appears in Stokes's theorem as this. Physically, the curl equals the line integral of f around an area divided by the area in the limit where the area becomes infinitesimal. Since the line integral of an electrostatic field E around an enclosed path is 0, Stokes' theorem implies that curl E equals 0. See Appendix F for a discussion of the various vector operators in different coordinate systems. And then we're off with our list of problems. And then the exercises, which don't come with solutions in this book. The solutions are in the instructor's manual, which is hard to acquire. All right, chapter 3, electric fields around conductors. In the first two chapters, we were concerned with the electric field and potential due to charges whose positions were fixed and known. We will now study the field and potential due to charges on conductors, where the charges are free to move around. This is a more difficult task because on one hand we need to know the field to determine the positions of the charges, but on the other hand we need to know the positions of the charges to determine the field. Fortunately, there are some facts and theorems that make this tractable, and indeed in some cases trivial. The most important fact is that in an electrostatic setup, the electric field inside the material of a conductor is 0. Equivalently, all points in a given conductor have the same potential. This leads to the somewhat surprising effect called electrical shielding. The electric field inside an empty conducting shell is 0, independent of whether arbitrary charge distribution exists outside. We proved the very helpful uniqueness theorem, which states that, given the values of the potential phi on the surfaces of a set of conductors, the solution for phi through space is unique. This theorem often makes things so easy that you may wonder if you're actually cheating. A byproduct of the theorem is the topic of image charges, which allow us to construct the electric field near conductors in certain cases. We define the capacitance coefficients of a set of conductors. These tell us how much charge resides on a conductor at a given potential. Capacitors are a fundamental circuit element, as we will see in Chapter 8. Finally, we discuss the energy stored in a capacitor. Off we go. Conductors and insulators. Conductors in the electrostatic fields. The general electrostatic problem and the uniqueness theorem. Image charges. Capacitance and capacitors. Potentials and charges on several conductors. Energy stored in a capacitor. Other views of the boundary value problem. Applications. The purpose of a lightning rod on a building is to provide an alternative path for the lightning's current on its way to ground. That is, a path that travels along a metal rod as opposed to through the building itself. Should the tip of the rod be pointed or rounded? The larger the field generated by the tip, the better the chance that a conductive path for the lightning is formed, meaning that the lightning is more likely to hit the rod than some other point on the building. On one hand, a pointed tip generates a large electric field close to the tip, but on the other hand, the field falls off more quickly than the field due to a more rounded tip. You can model the tip roughly as a small sphere. It isn't obvious which of these effects wins, but experiments suggest that a somewhat rounded tip has a better chance of being struck. Capacitors have many uses. We will look at a few here. Capacitors can be used to store energy for either slow discharge or fast discharge. In the slow case, the capacitor acts effectively like a battery. Examples include shake flashlights and power adapters. For the fast case, capacitors also have the ability to release their energy very quickly, unlike a normal battery. Examples include flash bulbs, stun guns, defibrillators, and the National Ignition Facility. Actually, that reminds me, this defibrillator and stun gun, I saw this thing today from Big Clive. Do you know Big Clive? He makes videos about electronics like I do, but I think he knows more about it than I do as well. So I'm going to put Big Clive stun gun. He takes a taser apart. Apparently he's not allowed to buy them where he lives, and he must have been in the States or he's ordered one or something. Anyway, he's managed to get one. I'll put the link in the show notes. Sorry, that stun gun, the reference to the stun gun just made me think of it. So whose goal is to create sustained fusion? The capacitor for a flash bulb might store 10 joules of energy, while the huge capacitor bank at the NIF can store 10 to the power of 8. Wow, that's a lot, joules. It's not 1.2 1.21 gigawatts. It's not, is it? Is it 0.0000000068678? It's K meg. Yeah, it's 0.4. Not gigawatts, gigajoules. Okay. All right. Sorry about that. Let's carry on. In many electronic devices, capacitors are used to smooth out fluctuations in the voltage in a DC circuit. If a capacitor is placed in parallel with the load, it acts like a reverse battery. If the voltage from the power supply dips, the capacitor will temporarily continue to push current through the load. The dynamic random access memory, DRAM, in your computer works by storing charge on billions of tiny capacitors. Each capacitor represents a bit of information. Uncharged is 0, charged is 1. However, the capacitors are leaky, so their charges must be refreshed many times each second. 64 milliseconds is a common refresh time, hence the adjective dynamic. The memory is lost when the power is shut off. The permanent memory on the hard disk must therefore use a different method, the orientation of tiny magnetic domains, as we will see in Chapter 11. Capacitors are also used for tuning electronic circuits. We will see in Chapter 8 that the resonant frequency of a circuit containing a resistor, inductor, and capacitor depends on the inductance and capacitance. Radios, cell phones, wireless computer connections, etc. function by changing the capacitance of an internal circuit so that the resonant frequency equals the frequency of the desired signal transmitted by an electromagnetic wave, which will be discussed in Chapter 9. Capacitors can be used in power factor correction in the AC electrical power grid. We will talk about AC circuits in Chapter 8, but the main point is that by adding capacitors or inductors to a load, a larger fraction of the power delivered can actually be used instead of sloshing back and forth between the power station and the load. This sloshing wastes energy by heating up the transmission lines. A condenser microphone makes use of the fact that the capacitance of a parallel plate capacitor depends on the plate separation. Condenser is simply another name for capacitor. A small capacitor consists of a fixed plate and a movable diaphragm. The pressure from the sound waves in the air moves the diaphragm back and forth, changing the separation and hence the capacitance. This movement is extremely small but is large enough to affect a circuit and generate an electric signal that can be sent to a speaker. Due to the large resistance of the circuit, the charge on the capacitor remains essentially constant as the diaphragm vibrates back and forth. So the voltage charge changes only because the capacitance changes. That is phi equals QO on C. By the way, there are electret microphones which have a permanent static charge, and then the actual good quality condenser microphones that they use in like recording studios and stuff, they have a thing called phantom voltage, which is additional power that's used to power the condenser or the capacitor that's used in the microphone. There you go. So that's what an electret microphone, when you hear that, that's what they're talking about. They're talking about a permanent charge on the piezoelectric thing that gets put there, and it only lasts for like 10 or 15 years. So if you have an old electret microphone, it might stop working because it lost its charge. Isn't that fascinating? A supercapacitor has a capacitance vastly larger than what can be produced by a pair of parallel plates. A supercapacitor with the dimensions of a standard D-cell battery can have a capacitance of well over a farad and even up to a kilofarad range. Two square plates separated by 1 millimeter would need to be 10 kilometers on a side to have an epsilon 0 A on S capacitance of 1 farad. A supercapacitor works by effectively making a very large and S very small. Two pieces of carbon foam are separated by an insulating membrane and immersed in an electrolyte solution. Other types, for example ones using graphene layers, also exist. The effective area A is large due to the porous nature of the foam, and the effective distance S is small, on the order of an atomic length, due to the fact that the electrolyte touches the foam. The voltage is generally only a few volts, so a supercapacitor is used when there is need for a steady supply of energy as opposed to a burst of energy. That is, it is used as a battery, although often short-lived, on the order of a minute, instead of, say, a flashbulb capacitor. The charging time of a supercapacitor is also on the order of a minute, much faster than a conventional battery. They actually use them in the OG Xbox. The OG Xbox has a supercapacitor that's used to keep your settings and the clock and that sort of thing active while you throw it in your bag and take it to your mate's house. But it doesn't keep time for very long. You have to plug it back in after a couple of hours. Chapter summary. Assuming there are no other forces involved, the electric field is zero within the material of a conductor in the stationary state. Equivalently, the conductor is an equipotential. Just outside the conductor, the field is perpendicular to the surface and has magnitude E equals, is that delta? Epsilon 0 from Gauss's law. The uniqueness theorem states that for a set of conductors at given potentials, the solution for the potential phi xyz is unique. This implies that once we have found a solution, by whatever means, we know that it must be the solution. A quick corollary is that if the space inside a hollow conductor of any shape is empty of charge, the electric field there is zero. If a given charge Q is located inside a conducting shell, then a total charge of negative Q resides on the inner surface of the shell. Any additional charge resides on the outer surface, and it distributes itself in the same manner as if neither the given charge Q nor the inner surface charge negative Q were present. These results follow from Gauss's law and the fact that the electric field is zero inside the material of the conductor. The method of image charges is useful for finding the electric field that satisfies a given set of boundary conditions at conductors. In the case of a point charge Q and an infinite conducting plane, the image charge negative Q is located on the other side of the plane, an equal distance from it. As expected from Gauss's law, the total charge on the plane is negative Q. The capacitance C, defined by Q equals C phi, gives a measure of how much charge a conductor can hold for a given potential phi. The capacitances of a sphere and a parallel plate capacitor are given as this, and the factors are what area and what's S? S is, I don't know, distance maybe, not sure. Yeah, it must be. S is the distance and or the displacement between the plates. If the I think epsilon 0 must be the is that the charge on an electron? It's the permittivity of free space. Permittivity of free space. If there are many conductors in a system, the charge on each is a linear function of the various potentials, with the coefficients of capacitance being the constants of proportionality. The energy stored in a capacitor can be written in several ways, including this, this, and this. There you go. And we're off to our problems. Chapter 4, Electric Currents. In this chapter, we discuss charge in motion, or electric current. The current density is defined as the current per cross-sectional area. It is related to the charge density by the continuity equation. In most cases, the current density is proportional to the electric field. The constant of proportionality is called the conductivity, and the inverse of the conductivity being the resistivity. Ohm's law gives an equivalent way of expressing this proportionality. We show in detail how the conductivity arises on a molecular level by considering the drift velocity of the charge carriers when an electric field is applied. We then look at how this applies to metals and semiconductors. In a circuit, an electromotive force, EMF, drives the current. A battery produces an EMF by means of chemical reactions. The current in a circuit can be found either by reducing the circuit via the series and parallel rules for resistors, or by using Kirchhoff's rules. The power dissipated in a resistor depends on the resistance and the current passing through it. Any circuit can be reduced to a Thevenin equivalent circuit involving one resistor and one EMF source. There's also the Norton equivalent, which is I think a parallel resistance and a current source. But let's not get ahead of ourselves. We end the chapter by investigating how the current changes in an RC circuit. Great. Water. All this talking really dries your mouth out. What was the first chapter called? Not the first chapter, the first section in this chapter. What was that called? Electric current and current density. Steady currents and charge conservation. Electrical conductivity and Ohm's law. The physics of electrical conduction. Currents and ions. Motion in zero electric field. Motion in non-zero electric field. Types of materials. Conduction in metals. Semiconductors. Circuits and circuit elements. Energy dissipation in current flow. Electromotive force and the voltaic cell. Networks with voltage sources. Applying Kirchhoff's rules. Thevenin theorem. Variable currents in capacitors and resistors. Applications. The transatlantic telegraph cable, see exercise 422, extended about 2,000 miles between Newfoundland and Ireland and was the most expensive and involved electrical engineering project of its time. After many failures, interrupted by a very short-lived success in 1858, it was finally completed in 1866. The initial failures were due partly to the fact that there didn't exist a consistent set of electrical units, in particular, a unit for resistance. A byproduct of the project was therefore the hastening of a consistent set of units. Electric shocks can range from barely noticeable to annoying to painful to lethal. The severity of a shock depends on the current, not the applied voltage. Although for a given resistance, a higher voltage means a higher current, of course. The duration also matters. The current can be harmful for two reasons. It can cause burns, and it can cause the heart to undergo fibrillation, where the normal coordinated contractions are replaced by uncoordinated ones, which don't pump any blood. Currents as small as 50 milliamps can cause fibrillation. A defibrillator works by passing a large enough current through the heart so that it briefly freezes up. With the uncoordinated contractions halted, the heart is then likely to start beating normally. A current of 10 milliamps running through your hand is roughly the can't let it go threshold, where the induced contractions of the muscles prevent you from letting go of the wire or whatever the voltage source is. And if you can't let go, you will eventually become sweaty, which will reduce the resistivity of your skin, making things even worse. People who work with electricity often keep one hand in their pocket to reduce the chance of it touching a grounded object and forming a conductive path, and even worse, a path that goes across the heart. If you touch a voltage source, the relation between the voltage and current depends on the resistance involved, and this can vary greatly depending on the conditions. The main things that the resistance depends on are the resistivity of your skin and the contact area. Dry skin has a much higher resistivity than wet skin. In a given scenario, the dry skin resistance might be, say, 100 kiloohms, whereas the wet skin resistance might be 1 kiloohm. The shock from a 120 volt wall socket in these two cases will be about 1 milliamp, hardly noticeable, or about 100 milliamps, potentially lethal. It's best to assume the latter. The variation of resistivity with the sweatiness of your skin is one of the ingredients in lie detector machines. The increase in current is quite remarkable, even if you don't think you're sweating much. If you hook yourself up to an apparatus of this sort, which can often be found in science museums and the like, and if you then imagine, say, bungee jumping off a high suspension bridge, the current will rise dramatically. It's like it is magically reading your mind. The wet interior of our bodies has an even lower resistivity, of course, so special precautions must be taken in hospital operating rooms. Even a small voltage across an exposed heart can create a sufficient current to cause fibrillation. If you shuffle your feet across a carpet on a dry day, you can get charged up to a very high voltage, perhaps 50,000 volts. If you then touch a grounded object, you get a shock in the form of a spark. But even if you're quite sweaty, this 50,000 volts certainly isn't lethal, whereas the 120 volts from the wall socket might very well be. As mentioned in section 218, the reason is that the amount of charge on you after shuffling across the carpet is very small, whereas there is an essentially infinite amount of charge available from the power company. The current in the case of the carpet lasts for a very short time before the charge runs out, and this time interval is too short to do any damage. A fuse is a safety device that protects against large currents in a circuit. 20 amps is a typical threshold. Such currents can generate enough heat to start a fire. A fuse consists of a thin strip of metal connected in series with the circuit. If the current becomes sufficiently large, the I2R resistance heating will melt the strip, producing a gap in the circuit and halting the current flow. A fuse needs to be replaced each time it burns out, but it's better to burn out a fuse than to burn down a house. A similar safety device, a circuit breaker, doesn't need to be replaced. It can simply be reset. This will be discussed in section 610. A smoke detector of the ionization type works by monitoring a tiny current. This current is created by a small radioactive source that emits alpha particles which ionize the air. These ions constitute the tiny current. When smoke enters the detector, the ions collect on the smoke particles and are neutralized. This disrupts the current, telling the alarm to go off. Electric eels can generate voltages on the order of 500 volts, which is enough to harm or possibly kill a human. The discharge is brief. A current of about 1 ampere lasts for a few milliseconds, but this is long enough. Special electrocyte cells, which take up most of the eel's body, are able to generate small voltages of roughly 0.1 of a volt by means of sodium-potassium pumps, a common mechanism in nerve and muscle cells. Indeed, we were reading about the sodium and potassium ions just earlier in the axons of the neuron. Thousands of these cells are stacked in series, the same basic idea behind a battery, to produce the 500 volt potential, and then many of these stacks are combined in parallel. The very tricky thing is for the eel to discharge all the electrocyte cells simultaneously. The mechanism for this isn't entirely understood. Sprites are faint flashes of light that sometimes occur high above thunderstorms. They are predominantly red and generally extend vertically, sometimes up to 100 kilometers. There are still many open questions about how they form, but an important fact is that the air is much less dense at high altitudes, so the breakdown field is lower. Electrons have more time to accelerate between collisions, so they can achieve higher speeds. A relatively small field, caused by a dipole distribution of charge in a thundercloud, can be large enough at high altitudes to cause breakdown. In a conductive metal wire, current can flow in either direction. The two directions are symmetrical. If you flip the wire over, it looks the same, but in a diode, current can flow in only one direction. A semiconductor diode consists of an N-type semiconducting region adjacent to a P-type region. The combination is called a P-N junction. The currents in these regions arise from the flow of electrons and holes, respectively. Because of this difference, there is an asymmetry between the two directions of current flow. This setup, therefore, has at least some chance of allowing current to flow in only one direction. And indeed, it can be shown that, provided the voltage isn't excessively large, current can flow only in the P to N direction, or equivalently, electrons can flow only from the N to P direction. The reasoning involves the diffusion of electrons and holes across the junction, which creates a depletion region where there are no mobile charge carriers. Alternatively, electrons can't flow from the P region to the N region because there are no mobile electrons in the P region to do the flowing. When a current flows through a diode, electrons give off energy by dropping from the conduction band down to a hole in the valence band. This energy takes the form of a photon, and for certain materials the energy gap corresponds to a photon whose frequency is in the visible spectrum. Such a diode is called a light-emitting diode, or LED. LEDs last much longer than incandescent bulbs, there is no filament that will burn out, and they are much more energy efficient. There is less wasted heat and fewer wasted photons in non-visible parts of the spectrum. They are also generally very small, so they can easily be inserted into circuits. A transistor is a device that allows a small signal in one part of a circuit to control a large current in another part. A transistor can be made with, for example, an NPN junction, although the middle region must be very thin for it to work. This is called a bipolar junction transistor, or a BJT. If two terminals are connected to the two N-type materials if two terminals are connected to the two N-type materials on the ends, no current will flow through the transistor because it effectively consists of two PN junctions. pointing in opposite directions. But if a small current is allowed to flow through the middle p-type material by way of a third terminal, then it turns out, although this is by no means obvious, that a much larger current will flow through the transistor, that is, through the original two terminals. A transistor can operate in an all or nothing mode, that is, as a switch that turns a large current on or off, or it can operate in a continuous manner where the resultant current depends on the small current in the middle p-type material, in which case, of course, it's an amplifier. Another type of transistor is the field effect transistor, the FET. There are different types of FETs, but in one type, a gate runs along the side of a p-type material. If I think is that an enhancement mode MOSFET? I'm not sure. If a positive voltage is applied to the gate, it will attract electrons and effectively turn a thin layer of the p-type material into n-type. If terminals are connected to two n-type regions that are placed at the ends of this layer, then we have a continuous n-type region running from one terminal to the other, so current can flow. Increasing the gate voltage increases the thickness of the n-type layer, thereby increasing the current flow between the terminals. The result is an amplification of the original signal to the gate, and indeed the transistor is the main component in the amplifier in your sound system. Although BGTs were developed first, FETs are by far the dominant transistor in modern electronics. There you go. Of course, hobbyists still use BJTs all over the place, but your CPU and all of the integrated circuits are made with FETs, MOSFETs, CMOS. Yeah, complementary metal oxide semiconductor. Solar cells produce power by making use of the photovoltaic effect. At a p-n junction of two semiconducting materials, an electric field naturally occurs due to the diffusion of electrons from the n to the p regions and of holes from the p to the n region. If photons in the sunlight kick electrons up to the conduction band, they, along with the holes created, will move under the force of the field and a current will be generated. Chapter summary. The current density associated with a given type of charge carrier is J equals NQU. Conservation of charge is expressed by the continuity equation, div J equals minus, is it delta rho on delta T, which is that delta? I'm not even sure. Which says that if the charge in a region decreases or increases, there must be current flowing out of or into that region. The current density in a conductor is related to the electric field by J equals that sigma E, where sigma is the conductivity. This implies a linear relation between voltage and current, known as Ohm's law. Tell you what I'm going to do. I'm going to make myself a coffee, and I'm going to make myself a cheat sheet that I can put up here. I've got up there is a old iPhone. I'm gonna put the Greek letters up there so I can say the right thing. So I'll be right back. All right. Well, I'm back, and I have a fresh coffee. Importantly, and I finished making that table. So I've made a list of the Greeks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 Greeks on one side, 12 on the other side. There's 24 letters in the Greek alphabet, 2 less than the Latin alphabet. And sigma, there's 2 ways of writing sigma. Oh, I called that delta earlier. I meant sigma. Anyway, when I see sigma, I just think standard deviation. Anyway, yeah, so I've got that. That's good. I guess we'll just go back to the beginning. I forget where I was up to with this chapter summary. And I've now got my table, so that's good to have. All right, let's get through this. Chapter summary. The current density associated with a given type of charge carrier is J equals NQU. Conservation of charge is expressed by the continuity equation. Div J equals delta rho. Yeah, that is rho. And what's this one? Maybe it's delta, although my delta looks a bit different to this. I don't know. Maybe it's just a Latin D. Is it just a D, like in dy dx or dx dy? I don't know. I don't know. My non-expert secret is out of the bag. Anyway, okay. Sorry, we were talking about this. So, blah, 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 blah. The current density in a conductor is related to the electric field by J equals sigma E, where sigma is the conductivity. This implies a linear relation between voltage and current known as Ohm's law, V equals IR. The resistance of a wire is R equals L on A sigma and rho L on A, where rho is the resistivity. An applied electric field results in a generally slow drift velocity of the charge carriers. The conductivity associated with the given type of charge carrier is sigma, approximately equivalent to NE squared tau. Is that tau? I believe it is. Tau, tau, tau. Yeah, lowercase tau on M, where tau is the mean time between collisions. Conduction in semiconductors arises from mobile electrons in the conduction band or mobile holes in the valence band. The former dominate in N-type semiconductors, while the latter dominate in P-type semiconductors. Doping can dramatically increase the number of electrons or holes. It is often possible to reduce a circuit of resistors to a smaller circuit via the rules for adding resistors in series and parallel. Okay, so they serially they add, and in parallel the inverses add, and the inverses are called the conductivity as opposed to the resistivity, as we mentioned earlier. Very good. More generally, the currents in a circuit can be found via Ohm's law with V equals IR and Kirchhoff's rules. Zero net current flow into any node and zero net voltage drop around any loop. The power dissipated in a resistor is given by P equals I squared R, which can also be written as IV or V squared on R. A voltaic cell or battery utilizes chemical reactions to supply an electromotive force. Since the line integral of the electric field around a complete circuit is zero, there must be locations where ions move against the electric field. The forces from the chemical reactions are responsible for this. Thevenin's theorem says that any circuit is equivalent to a single voltage source, epsilon EQ. I assume that's epsilon, is it? I don't know. It looks like maybe a lowercase epsilon. Sort of. Although that's what we had for the permittivity of free space, wasn't it? I don't know. Maybe it's just an E. I don't know. And a single resistor Req. The linearity of a circuit is critical in the proof of this theorem. If the charge on a capacitor is discharged across a resistor, the charge and current decrease exponentially with a time constant equal to RC. All right, now we're off. You can hear the birds out there this morning. Lovely Australian morning for you today. It's 6:48 a.m. I'm your host, JJ. I've been awake all night, drinking coffee and making videos for my YouTube channel. Chapter 5, The Fields of Moving Charges. The goal of this chapter is to show that when relativity is combined with our theory of electricity, a necessary conclusion is that a new force, the magnetic force, must exist. In non-static situations, charge is defined via a surface integral. With this definition, charge is invariant, that is, independent of reference frame. Using this invariance, we determine how the electric field transforms between two frames. We then calculate the electric field due to a charge moving with constant velocity. It does not equal the spherical symmetric Coulomb field. Interesting field patterns arise in cases where a charge starts or stops. The main result of this chapter, derived in section 5.9, is the expression for the force that a moving charge or a group of moving charges exerts on other moving charge. On our journey to this result, we will consider steps with increasing complexity. More precisely, in calculating the force on a charge Q due to another charge capital Q, there are 4 basic cases to consider depending on the charge's motions. 1. If both charges are stationary in a given frame, then we know from chapter 1 that Coulomb's law gives the force. 2. If the source Q is moving and lowercase q is at rest, then we can use the transformation rule for the electric field mentioned above. 3. If the source capital Q is at rest and lowercase q is moving, then we can use the transformation rule for the force presented in Appendix G to show that the Coulomb field gives the force as you would expect. 4. Finally, the case we are most concerned with, if both charges are moving, then we will show in section 5.9 that a detailed consideration of the relativistic effects implies that there exists an additional force that must be added to the electrical force. This is the magnetic force. Isn't that cool? From Ørsted to Einstein, magnetic forces, measurement of charge in motion, invariance of charge, electric field measured in different frames of reference, field of a point charge moving with constant velocity, field of a charge that starts or stops, force on a moving charge, interaction between a moving charge and other moving charges, chapter summary. Don't we usually have our applications before the chapter summary? Maybe I missed a page. Maybe not. Or maybe there are no applications for this chapter. What do you think? Chapter 5. Let me just jump to the table of contents. I'm a bit confused about that. Oh, there you go. No applications for chapter 5. That explains that. So we're straight into the chapter summary. Charged particles in a magnetic field experience a magnetic force equal to F equals QV by B. Okay. Gauss's law Q equals epsilon 0, which is the permittivity of free space, with the integral of is that the electric field, dA? I'm not sure what that means. Is A acceleration of something? I'm not sure. Holds for moving charges by the definition of charge, as well as for stationary charges. Charge is invariant, that is, the amount of charge in a system is independent of the frame in which it is measured. The total charge enclosed in a volume is independent of the motion of the charge carriers within. Consider a collection of charges which are at rest with respect to each other, moving with respect to the lab frame. These charges are the source of an electric field. The longitudinal component of this electric field is the same in the source frame and the lab frame, but the transverse component is larger in the lab frame. That is, it is smaller in the source frame than in any other frame. The field of a point charge moving with constant velocity, v equals beta c, is radial and has magnitude as given. If the charge stops moving, the field outside an expanding shell is the same as if the charge had kept moving, as indicated in figure 519. If a particle moves with respect to the lab frame, then the longitudinal component of the force on it is the same in its frame and the lab frame, but the transverse component is smaller in the lab frame. That is, it is larger in the particle frame than in any other frame. The force on a charge Q moving through an electric field E arising from stationary charges is simply QE, as one would expect. If a charge is moving with respect to other charges that are also moving in the lab frame, say in a wire, then the charge experiences a magnetic force. This magnetic force can alternatively be viewed as an electric force on the particle's frame. This non-zero electric field is due to the different length contractions of the positive and negative charges in the wire. In this manner, we see that magnetism is a relativistic effect. Wow, isn't that cool? I didn't know that. The magnetism happens because they have to keep the charge invariant. Huh. All right, chapter 6, the magnetic field. Having shown in chapter 5 that the magnetic force must exist, we will now study the various properties of the magnetic field and show how it can be calculated for an arbitrary, steady current distribution. The Lorentz force gives the total force on a charged particle as F equals QE plus QV times B. The results from the previous chapter give us the form of the magnetic field due to a long straight wire. This form leads to Ampere's law, which relates the line integral of the magnetic field to the current enclosed by the integration loop. It turns out that that Ampere's law holds for a wire of any shape. When supplemented with a term involving changing electric fields, this law becomes one of Maxwell's equations, as we will see in chapter 9. The source of magnetic fields are currents. The sources of magnetic fields are currents, in contrast with the sources of electric fields, which are charges. There are no isolated magnetic charges or monopoles. This statement is another of Maxwell's equations. As in the electric case, the magnetic field can be obtained from a potential, but it is now a vector potential. Its curl gives the magnetic field. The Biot-Savart law allows us to calculate, in principle, the magnetic field due to any steady current distribution. One distribution that comes up often is that of a solenoid, a coil of wire, whose field is essentially constant inside and zero outside. This field is consistent with an Ampere's law calculation of the discontinuity of B across a sheet of current. By considering various special cases, we derived the Lorentz transformations of the electric and magnetic fields. The electric or magnetic field in one frame depends on both the electric and magnetic fields in another frame. The Hall effect arises from QV times B part of the Lorentz force. This effect allows us for the first time to determine the sign and the charge carriers in a current. Then we're off. Chapter 6.1, section 6.1, definition of the magnetic field, which is B. I think they got B as the magnetic field, if I've read that right. Some properties of the magnetic field. Vector potential. Field of any current carrying wire. Fields of rings and coils. Change in B at a current sheet. Rowland's experiment. Electrical conduction in a magnetic field, the Hall effect, and applications. A mass spectrometer is used to determine the chemical makeup of a substance. Its operation is based on the fact that if a particle moves perpendicular to a magnetic field, the radius of curvature of the circular path depends on the particle's mass. See exercise 6.29. In the spectrometer, molecules in a sample are first positively ionized, perhaps by bombarding them with electrons, which knocks electrons free. The ions are accelerated through a voltage difference and then sent through a magnetic field. Lighter ions have a smaller radius of curvature. Even though lighter ions are accelerated to higher speeds, you can show that the magnetic field still bends them more compared with heavier ions. By observing the final positions, the masses, or technically the mass-to-charge ratios, of the various ions can be determined. Uses of mass spectroscopy include forensics, drug testing, testing for contaminants in food, and determining the composition of the atmosphere of planets. The image in an old television set made prior to the early 2000s is created by a cathode ray tube. The wide end of the tube is the television screen. Electrons are fired towards the screen and are deflected by the magnetic field produced by current-carrying coils. This current is varied in such a way that the impact point of the electrons on the screen traces out the entire screen many times per second via a sequence of horizontal lines. When the electrons hit the screen, they cause phosphor in the screen to emit light. A particular image appears depending on which locations are illuminated. The intensity of the electron beam is modulated to create the desired shading at each point, black, white, or something in between. Color TVs have 3 different electron beams for the 3 primary colors. Consider 2 coaxial solenoids with their currents oriented the same way, separated by some distance in the longitudinal direction. The magnetic field lines will diverge as they leave one solenoid, then reach a maximum width halfway between the solenoids, and then converge as they approach the other solenoid. Consider a charged particle moving approximately in a circle perpendicular to the field lines under the influence of the Lorentz force, while also drifting in the direction of the field lines. It turns out that the drifting motion will be reversed in regions where the field lines converge, provided that they converge quickly enough. The particle can therefore be trapped in what is called a magnetic bottle, bouncing back and forth between the ends. A bottle type effect can be used, for example, to contain plasma in fusion experiments. A magnetic bottle can also be created by the magnetic field due to a current ring. The ring effectively produces a curved magnet bottle. The field lines expand near the plane of the ring and converge near the axis. This is basically what the magnetic field of the Earth looks like. The regions of trapped charge particles are called the Van Allen belts. If particles approach the ends of the belt, that is, if they approach the Earth's atmosphere, the collision with the air molecules cause the molecules to emit light. We know this as the northern or southern lights, or alternatively as the aurora borealis or australis. The various colors come from the different atomic transitions in oxygen and nitrogen. The sources of the charged particles are solar wind and cosmic rays. However, the source can also be man-made. In 1962, high-altitude hydrogen bomb test, codenamed Starfish Prime, gave a wide area of the Pacific Ocean quite a light show. But at least people were warned about the test. The headline of the Honolulu Advertiser read, "End blast tonight may be dazzling, good view likely." The Earth's atmosphere protects us significantly from solar wind, consisting mostly of protons and electrons, and from the steady background of cosmic rays, consisting mostly of protons. But the Earth's magnetic field also helps out. The charged particles are deflected away from the Earth by the Lorentz force from the magnetic field. In the event of a severe solar flare, however, a large number of particles make it through the field, disrupting satellites and other electronics. Providing a way to shield astronauts from radiation is one of the main obstacles to extended space travel. Generating a magnetic field via currents in superconductors, see Appendix I, is a potential solution. Although this would certainly be expensive, propelling thick heavy shielding, the analog of Earth's atmosphere, into space would also be very costly. A railgun is a device that uses the QV times B Lorentz force instead of an explosive to accelerate a projectile. The gun consists of 2 parallel conducting rails with a conducting object spanning the gap between them. This object, which is the projectile, or perhaps a large object holding the projectile, is free to slide along the rails. A power source sends current down one rail, across the projectile, and back along the other rail. The current in the rails produces a magnetic field, and you can use the right-hand rule to show that the resulting Lorentz force on the projectile is directed away from the power source. Large-scale railguns can achieve projectile speeds of a few kilometers per second and have a range of hundreds of kilometers. Wow. In one form of electric motor, a DC current flows through a coil that is free to rotate between the poles of a fixed magnet. The Lorentz force on the charges moving in the coil produces a torque, see exercise 634, so the coil is made to rotate. Alternatively, the coil behaves just like a magnet and north and south poles, and this magnet interacts with the field of the fixed magnet. The coil can then apply a torque to whatever object the motor is attached to. There are both AC and DC motors and different kinds of each. In a brushed DC motor, a commutator causes the current to change direction every half cycle so that the torque is always in the same direction. If for some reason the motor gets stuck and stops rotating, the back EMF, which we will learn about in chapter 7, drops to 0. The current through the coil then increases, causing it to heat up. The accompanying smell will let you know that you're in the process of burning out your motor. Solenoids containing superconductive, there's a, I forget what you call it, but you can actually put it in a diode to limit that back EMF. And it just, instead of frying your motor, it just, I don't know, it flows through the diode and heats up, but doesn't get, I don't know, doesn't get high current. Solenoids containing superconducting wires can be used to create very large fields on the order of 20 Tesla. The superconducting, is it Tesla? I believe it is. The superconducting wires allow a large current to flow with no resistive heating. A magnetic resonance imaging MRI machine uses the physics described in Appendix J to take image of the inside of your body. Its magnetic field is usually about 1 or 2 Tesla. The magnets in the Large Hadron Collider at CERN are also superconducting. If a defect causes the circuit to become non-superconducting, a result known as quench, then the circuit will heat up rapidly and a chain reaction of very bad things is likely. As we will see in chapter 7, solenoids store energy and this energy needs to go somewhere. In 2008 at CERN, a quench caused major damage and took the accelerator offline for a year. Oh wow, gee, this chapter is long. We've already did a couple of pages. The size of the magnetic field in a superconducting solenoid is limited by the fact that a superconducting wire can't support magnetic fields or electric currents above certain critical values. The largest sustained magnetic fields in a laboratory are actually created with resistive conductors. All right. The optimal design has the coils of the solenoid placed by bitter plates arranged in a helical pattern. These plates operate in basically the same manner as coils, but they allow for water cooling via well-placed holes. A bitter magnet, which can achieve a field of about 35 Tesla, requires a serious amount of water cooling, around 100 gallons per second. If a coil of wire is wrapped around an iron core, the core's magnetic field is magnified by the iron for reasons we will see in chapter 11. The magnification factor can be 100 or 1000 or even larger. This magnification effect is used in relays, circuit breakers, junkyard magnets, all discussed below, and many other devices. The combination of a coil and an iron core, or even a coil without a core, is called an electromagnet. The main advantage of an electromagnet over a permanent magnet is that the field can be turned on and off. An electric relay is a device that uses a small signal to switch on or off a larger signal. So a relay and a transistor act in the same manner. Not the same manner. A small current in one circuit passes through an electromagnet. The magnetic field of this electromagnet pulls on a spring-mounted iron lever that closes or opens a second circuit. The power source in this second circuit is generally much larger than in the first. A relay is used, for example, in conjunction with a thermostat. A small current in the thermostat's temperature sensor switches on a much larger current in the actual heating system, which involves, say, a hot water pump. In years past, relays were used at telegraph repeaters. That relay took a weak incoming signal at the end of a long wire and automatically turned it into a stronger outgoing signal, thereby eliminating the need for a human being to receive and retransmit information, and of course leading to it being called a relay. A circuit breaker is similar to a fuse, see section 412, in that it prevents the current in a circuit from becoming too large. 15 amps or 20 amps are typical thresholds for a household circuit breaker. in the USA, where the line voltage is 120 volts. In Australia, where it's 230 or nominally, or 240 in practice, it's actually 10 amps, but that's essentially the same. If you are running many appliances in your home at the same time, the total current may be large enough to cause a wire somewhere inside a wall to overheat and start a fire. Similarly, a sustained short circuit will almost certainly cause a fire. One type of circuit breaker contains an electromagnet whose magnetic field pulls on an iron lever. The lever is held in place by a spring, but if the current in the electromagnet becomes sufficiently large, the force on the lever is large enough to pull it down away from its resting position. This movement breaks the circuit in one way or another, depending on the design. The circuit breaker can be reset by simply flipping a switch that manually moves the lever back to its resting position. This should be contrasted with a fuse, which must be replaced each time it burns out. Junkyard magnets can have fields in the 1 Tesla range. This is fairly large, but the real key to the magnet's strength is its large area, which is on the order of a square meter. If you've ever played with a small rare earth magnet with a field of around 1 Tesla, felt how strongly it can stick to things, imagine playing with one that is a meter in diameter. It's no wonder it can pick up a car. Doorbells, or at least those of the ding-dong type, consists of a piston located inside a solenoid. Part of the piston is a permanent magnet. A spring holds the piston off to one side, say to the left, where its left end rests on the soundbar. When the doorbell button is pressed, the circuit is completed and the current flows through the solenoid. The resulting magnetic field pulls the piston through the solenoid and causes the right end to hit another soundbar located off to the right. This is the ding bar. As long as the button is held down, the piston stays there, but when the button is pressed, the current stops flowing in the solenoid and the spring pushes the piston back to its initial position where it strikes the left soundbar, the dong bar. The speakers in your sound system are simple devices in principle, although they require a great deal of engineering to produce a quality sound. A speaker converts an electrical signal into sound waves. A coil of wire is located behind a movable cone, the main part of the speaker that you see, also called the diaphragm, and attached to its middle. The coil surrounds one pole of a permanent magnet and is in turn surrounded by another pole. Imagine a stamp/cutter for making donuts. The coil is free to slide along the inner cylinder of the stamp. Depending on the direction of the current in the coil, the permanent magnet pushes the coil and hence the cone one way or the other. The movement of the cone produces the sound waves that travel to your ears. If the correct current with the proper time varying amplitude to control the volume and frequency to control the pitch is fed through the coil, the cone will oscillate in exactly the manner needed to produce the desired sound. Audible frequency range from 20 Hz to 20 kHz, so the oscillations will be quick. The necessary current originates in a microphone, which operates in the same way as a speaker, but in reverse. That is, well, some of them do. That is, a microphone converts sound energy into an electrical signal. There are many different types of microphones. We talked about one in section 3.9, and we will talk about another in section 7.11 after we have covered electromagnetic induction. Maglev trains, short for magnetic levitation, are vertically supported, laterally stabilized, and longitudinally accelerated by magnetic fields. The train has no contact with the track, which means it can go faster than a conventional train. Speeds can reach 500 km per hour or 300 miles per hour. There is also less wear and tear. There are two main types of maglev trains: electromagnetic suspension, EMS, and electrodynamic suspension, EDS. The EMS system makes use of both permanent magnets and electromagnets. The lateral motion of the train is unstable, so sensitive computerized correction is required. The EDS system makes use of electromagnets, in some cases involving superconductors, along with the magnetic induction discussed in Chapter 7. An advantage of EDS is that the lateral motion is stable, but a disadvantage is that the stray magnetic fields inside the cabin can be fairly large. Additionally, an EDS train requires minimum speed to levitate, so wheels are needed at low speeds. The propulsion mechanism in both systems involves using alternating current to create magnetic fields that continually accelerate or decelerate the train. All maglev trains require a specially built track, which is a large impediment to adoption. And now we're up to our chapter summary. The Lorentz force on a charged particle in an electromagnetic field is given. The magnetic field due to a current in a long straight wire points in the tangential direction and has magnitude as given. If a wire carrying I2 dies perpendicular to a magnetic field B1, did I say dies? Yeah, I did. I mean, it meant lies. If a wire carrying current I2 lies perpendicular to a magnetic field B1, then the magnitude of the force on a length L of the wires is F equals I2 B1L. The SI and Gaussian units of magnetic field are the Tesla and Gauss, respectively. 1 Tesla equals exactly 10 to the power 4 Gauss. Ampere's law in integral and differential forms is given. The magnetic field also satisfies this expression. This is the statement that there are no magnetic monopoles, or equivalently that magnetic field lines have no endings. The vector potential A is defined by this, which leads to this being identically true. Given the current density J, the vector potential can be found this way. The contribution to the magnetic field from a piece of wire carrying current I is given by the Biot-Savart law. This law is valid for steady currents. The field due to an infinitely long solenoid is 0 outside and has magnitude B equals mu O N I inside, where N is the number of turns per unit length. If a sheet of current has current density J, then the change in B across the sheet is delta B equals mu OJ. If it is a J, I don't know. The Lorentz transformations give the relations between E and B fields in two different frames, as given, where V is the velocity of the frame F prime with respect to frame F. If there exists a frame in which B equals 0, for example, if all the charges are at rest in one frame, then B prime is given in all frames. Similarly, if there exists a frame in which E equals 0, for example, the frame of a neutral current carrying wire, then E prime equals V times B prime in all frames. Henry Rowland demonstrated that a magnetic field is produced not only by a current in a wire, but also by the overall motion of an electrostatically charged object. In the Hall effect, an external magnetic field causes the charge carriers in a current-carrying wire to pile up on one side of the wire. This causes a transverse electric field inside the wire. For most purposes, a current of negative charges moving in one direction acts the same as a current of positive charges moving in the other direction, but the Hall effect can be used to determine the sign of the actual charge carriers. There you go. I have Hall effect magnetic sensors in my drawer, so that is something that continues to be exploited in contemporary reality. But I think it was found a long time ago, the Hall effect. But it probably took them a while to tool up the manufacturing plants that churn them out for pennies. All right, chapter 7, electromagnetic induction. In this chapter, we study the effects of magnetic fields that change with time. Our main result will be that a changing magnetic field causes an electric field. We begin by using the Lorentz force to calculate the EMF around a loop moving through a magnetic field. We then make the observation that this EMF can be written in terms of the rate of change of the magnetic flux through the loop. The sign of the induced EMF is determined by Lenz's law. If we shift frames so that the loop is now stationary and the source of the magnetic field is moving, we obtain the same result for the EMF in terms of the rate of change of flux as expected. Faraday's law of induction states that this result holds independent of the cause of the flux change. For example, it applies to the case in which we turn a dial to decrease the magnetic field while keeping all objects stationary. The differential form of Faraday's law is one of Maxwell's equations. Mutual inductance is the effect by which changing current in one loop causes an EMF in another loop. This effect is symmetrical between the two loops, as we will prove. Self-inductance is the effect by which a changing current in a loop causes an EMF in itself. The most commonly used object with self-inductance is a solenoid, which we call an inductor, symbolized by L. The current in an RL circuit changes in a specific way, as we will discover. The energy stored in an inductor equals Li squared on 2, which parallels the CV squared on 2 energy stored in a capacitor. Similarly, the energy density in a magnetic field equals B squared on 2 mu O. What is mu O? Is that it's the permeability of free space, which parallels the epsilon 0 E squared energy density in the electric field. Okay, so the electric field is the permittivity and the magnetic field is the permeability. All right, and we're off. Faraday's discovery. Michael Faraday's account of the discovery of electromagnetic induction begins as follows. 1. The power which electricity of tension possesses of causing an opposite electrical state in its vicinity has been expressed by the general term induction, which, as it has been received into scientific language, may also, with propriety, be used in the same general sense to express the power which electrical currents may possess of inducing any particular state upon matter in their immediate neighbourhood, otherwise indifferent. It is with this meaning that I propose to use it in the present paper. Certain effects of the induction of electrical currents have already been recognized and described, as those of magnetization, Ampere's experiments of bringing a copper disc near to a flat spiral, his repetition with electromagnets of Arago's extraordinary experiments, and perhaps a few others. Still, it appeared unlikely that these could be all the effects which induction by currents could produce, especially as, upon dispensing with iron, almost the whole of them disappear, whilst yet an infinity of bodies exhibiting infinite phenomena of induction with electricity of tension still remain to be acted upon by the induction of electricity in motion. 3. Further, whether Ampere's beautiful theory were adopted or any other, or whatever reservation were mentally made, still it appeared very extraordinary that as every electric current was accompanied by a corresponding intensity of magnetic action at right angles to the current, good conductors of electricity, when placed within the sphere of this action, should not have any current induced through them, or some sensible effect produced equivalent in force to such a current. These considerations, with their consequence, the hope of obtaining electricity from ordinary magnetism, have stimulated me at various times to investigate experimentally the inductive effect of electric currents. I lately arrived at positive results, and not only had my hopes fulfilled, but obtained a key which appeared to me to open out a full explanation of Arago's magnetic phenomena, and also to discover a new state which may probably have great influence in some of the most important effects of electric currents. 5. These results I purpose describing, not as they were obtained, but in such a manner as to give the most concise view of the whole. This passage was part of the paper Faraday presented in 1831. It is quoted from his Experimental Researches in Electricity, published in London in 1839. Faraday, 1839. There follows in the paper a description of a dozen or more experiments through which Faraday brought to light every essential feature of the production of electric effects by magnetic action. By electricity in tension, Faraday meant electrostatic charges, and the induction he refers to in the first sentence involved nothing more than we have studied in Chapter 3, that the presence of a charge causes a redistribution of charges on conductors nearby. Faraday's question was, why does an electric current not cause another current in nearby conductors? Okay. Conducting rod moving through a uniform magnetic field, loop moving through a non-uniform magnetic field, stationary loop with the field source moving, universal law of induction. Mutual inductance. Pages are a bit sticky. A reciprocity theorem, self-inductance, circuit containing self-inductance, energy stored in the magnetic field, and applications. An electrodynamic tether is a long, perhaps 20-kilometer straight conducting wire that has one end connected to a satellite. The other end hangs down towards or up away from the Earth. As the satellite and the tether orbit the Earth, they pass through the Earth's magnetic field. Just as with the moving rod in section 7.2, an EMF is generated along the wire. If this were the whole story, charge would simply pile up on the ends, but the satellite is moving through the ionosphere, which contains enough ions to yield a return path for the charge. A complete circuit is therefore formed, so the EMF can be used to provide power to the satellite. However, the current in the wire will experience a Lorentz force, and you can show that the direction is opposite to the satellite's motion. On the other hand, if a power source on the satellite drives current in the opposite direction along the tether, the Lorentz force will be in the same direction as the satellite's motion, so the tether can serve as a gentle propulsion device. If you drop a wire hoop into a region containing a horizontal magnetic field, the changing flux will induce a current in the hoop. From Lenz's law and the right-hand rule, the resulting Lorentz force on the current is upward, depending on whether the hoop is entering or leaving the region of the magnetic field. So the direction of the force is always opposite to that of the velocity. If you drop a solid metal sheet into the region, loops or eddies of current will develop in the sheet, and the same braking effect, known as eddy current braking, will occur. This braking effect has many applications, from coin vending machines to trains to amusement park rides. The loss in kinetic energy shows up as resistive heating. Eddy currents are also used in metal detectors, both of the airport security type and the hunting for buried treasure type. The metal detector sends out a changing magnetic field which induces eddy currents in any metal present. These currents produce their own changing magnetic field, which is then detected by the metal detector. An electric guitar generates its sound via magnetic induction. The strings are made of a material that is easily magnetized, and they vibrate back and forth above pickups. A pickup is a coil of wire wrapped around a permanent magnet. This magnet causes the string to become magnetized, and the string's magnetic field then produces a flux through the coil. Because the string is vibrating, this flux is changing, so an EMF is induced in the coil. This sends an oscillating current with the same frequency as the string's vibration to an amplifier, which then amplifies the sound. Without the amplifier, the sound is barely audible. Electric guitars with nylon or otherwise non-magnetic strings wouldn't work. A shake flashlight is a nice application of Faraday's law. As you shake the flashlight, a permanent magnet passes back and forth through a coil. The induced EMF in the coil produces a current that deposits charge on a capacitor where it can be stored. A bridge rectifier, consisting of a certain configuration of 4 diodes, changes the alternating current EMF from your shaking motion to a direct current EMF, so that positive charge always flows toward the positive end of the capacitor, independent of which way the magnet is moving through the coil. When you flip the light switch to allow current to flow from the capacitor through the light bulb. An electric generator is based on the circuit in figure 7.13. An external torque causes the loop of wire to rotate, and the changing flux through the loop induces an oscillating, that is, alternating EMF. In practice, however, in most generators, the rotating part, which is effectively the turbine, contains a permanent magnet that produces a changing flux through coils of wire arranged around the perimeter. In any case, it is Faraday's law at work. The force causing the turbine to rotate can come from various sources: water pressure from a dam, air pressure on a mill, steam pressure from a coal plant or nuclear reactor, etc. The alternator in a car engine is simply a small electric generator. In addition to turning the wheels, the engine also turns a small magnet inside the alternator, producing an alternating current. However, the car's battery requires direct current, so a rectifier converts the AC to DC. On an even smaller scale, the magnet on one type of bicycle light generator is made to rotate due to the friction force from the tire. The power generated is usually only a few watts, a small fraction of the total power output from the rider. But don't think that you could make much money by harnessing all of your power on a stationary bike. If a professional cyclist sold the power he could generate during 1 hour of hard pedaling, he would earn about 5 cents. Hybrid cars, which are powered by both gasoline and a battery, use regenerative braking to capture the kinetic energy of the car when the brakes are applied. The motion acts as a generator. More precisely, the friction force between the tires and the ground provides torque on the gears in the motor, which in turn provide a torque on the magnet inside the generator. A microphone is basically the opposite of a speaker. See section 610. It converts sound waves into an electrical signal. A common type, called a dynamic microphone, makes use of electromagnetic induction. A coil of wire is attached to a diaphragm and surrounds one pole of a permanent magnet in the same manner as a speaker. When a sound wave causes the diaphragm to vibrate, the coil likewise vibrates. Its motion through the field of the magnet causes changing flux through the coil. An EMF and hence current are therefore induced in the coil. This current signal is sent to a speaker, which reverses the process, turning the electrical signal back into sound waves. Alternatively, the signal is sent to a device that stores the information. See the discussion of cassette tapes and hard disks in section 11.12. A ground fault. Cassette tapes is dating himself there, isn't he? A ground fault circuit interrupter, GFCI, helps prevent or at least mitigate electrical shocks. Under normal conditions, the current coming out of the hot slot in a wall socket, the short slot, equals the current flowing into the neutral slot, the tall slot. Now, let's say you are receiving an electric shock. In a common type of shock, some of the current is taking an alternate route to ground, through you instead of through the neutral wire. The GFCI monitors the difference between the currents in the hot and the neutral wires. If it detects a difference of more than 5 or 10 milliamps, it trips the circuit quickly in about 30 milliseconds. This monitoring is accomplished by positioning a toroidal coil around two wires to and from the slots. The current in these wires travel in opposite directions, so when the currents agree, there is zero net current in the pair. But if there is a mismatch in the oscillating currents, then the non-zero net current will produce a changing magnetic field circling around the wires. So there will be a changing magnetic field in the toroidal coil, which will induce a detectable current in the coil. A signal is then sent to a mechanism that trips the circuit. Having survived a shock, you can reset the GFCI by pressing the reset button on an outlet. As with a circuit breaker, see section 610, nothing needs to be replaced after the circuit is tripped. In contrast, a fuse, see section 412, needs to be replaced after it burns out. However, the purpose of a GFCI is different. A GFCI protects people by preventing tiny currents from traveling through them. Even 50 milliamps can disrupt the functioning of a part, while a fuse or a circuit breaker protects buildings by preventing large currents on the order of 20 amps, which can generate heat and cause fires. A transformer changes the voltage in a circuit. Imagine two solenoids, A and B, both wound around the same cylinder. Let B, the secondary winding, have 10 times the number of turns as A, the primary winding. If a sinusoidal voltage source is connected to A, it will cause a changing flux through A and hence through B, and the latter flux being 10 times the former. The induced EMF in B will therefore be 10 times the EMF in A. By adjusting the ratio of the number of turns, the voltage can be stepped up or stepped down by any factor. In practice, the solenoids in a transformer aren't actually right on top of each other, but instead wrapped around different parts of an iron core, which funnels the magnetic field lines along the core from one solenoid to the other. The ease with which AC voltages can be stepped up or down is the main reason why the electric grid uses AC. It is necessary to step up the voltage for long distance transmission and hence step down the current for a given value of power, P equals IV. because otherwise there would be prohibitively large energy losses due to the I squared R resistance heating in the wires. An ignition system coil in your car converts the 12 volts from the battery into the 30,000 or so volts needed to cause the arcing or spark across the spark plugs. Like a transformer, the ignition coil has primary and secondary windings, but the mechanism is slightly different. Instead of producing an oscillating voltage, it produces a one-time surge in voltage, whose original source was the 12-volt DC battery. It does this in two steps. First, the battery produces a steady current through a circuit containing the primary winding. A switch is then open and the current drops rapidly to zero. The rate is controlled by inserting a capacitor in the circuit in parallel with the switch. This change in current creates a large back EMF in the primary coil, say 300 volts. Second, if the secondary winding has, say, 100 times as many turns as the primary, then the transformer reasoning in the preceding paragraph leads to 30,000 volts in the secondary coil. This is enough to cause arcing in the spark plug. This two-step process means that we don't need to have 30,000 divided by 12 approximately equals 3,000 as many turn in the secondary coil. Oh, I see. Wow. A boost converter or step-up converter increases the voltage in a DC circuit. It is used, for example, to power a 3-volt LED lamp with a 1.5 battery. 1.5 volt battery. The main idea behind the converter is the fact that inductors resist sudden changes in current. Instead, a circuit where current flows from a battery through an inductor. If a switch is opened downstream from the inductor, and if an alternative path is available through a capacitor, the current will still flow for a brief time through the inductor into the capacitor. Charging will therefore build up on the capacitor. This process is repeated at a high frequency, perhaps 50 kilohertz. Even if the back voltage from the capacitor is higher than the forward voltage from the battery, a positive current will still flow briefly onto the capacitor each time the switch is open. Backward current can be prevented with a diode. The capacitor then serves as a higher voltage effective battery for powering the LED. The magnetic field of the Earth cannot be caused by a permanent magnet because the interior temperature is far too hot to allow the iron core to exist in a state of permanent magnetization. Instead, the field is caused by the dynamo effect. See problem 719 and exercise 747. A source of energy is needed to drive the dynamo, otherwise the field would decay on a timescale of 20,000 years or so. This source isn't completely understood. Possibilities include tidal forces, gravitational setting, radioactivity, and the buoyancy of lighter elements. The dynamo mechanism requires a fluid region inside the Earth. This region is the outer core, and also a means of charge separation, perhaps friction between layers, so that currents can exist. It also requires that the Earth be rotating so that the Coriolis force can act on the fluid. Computer models indicate the motion of the fluid is extremely complicated, and also that the reversal of the field, which happens every 200,000 years on average, is likewise complicated. The poles don't simply rotate into each other. Rather, all sorts of secondary poles appear on the surface of the Earth during the process, which probably takes a few thousand years. Who knows where all the famous explorers and their compasses would have ended up if a reversal had been taking place during the last 1,000 years. In recent years, the magnetic North Pole has been moving at the brisk rate of about 50 kilometers per year. This speed isn't terribly unusual though, so it doesn't necessarily imply that a reversal is imminent. Chapter summary. Faraday discovered that a current in one circuit can be induced by a changing current in another circuit. If a loop moves through a magnetic field, the induced EMF equals, is that epsilon again? I'm not sure. It's like a big epsilon. I don't know. VW B1 minus B2, where W is the length of the transverse side and the B's are the fields at these sides. This EMF can be viewed as a consequence of the Lorentz force acting on the charges in the transverse sides. More generally, the EMF can be written in terms of the magnetic flux. This is known as Faraday's law of induction, and it holds in all cases. The loop can be moving, or the source of the magnetic field can be moving, or the flux can be changed by some other arbitrary means. The sign of the induced EMF is determined by Lenz's law. The induced current flows in the direction that produces a magnetic field that opposes the change in flux. The differential form of Faraday's law is given. This is one of Maxwell's equations. If we have two circuits, C1 and C2, and current I1 in one circuit will produce a flux phi 21 through the other, the mutual inductance M21 is defined by M21 equals, is that phi again? Yeah, capital phi. Pardon me. I'm out of coffee. I'm going to get more coffee. All right, I'm back for fresh coffee. Keep your nerds caffeinated. We're about halfway through, so it's going to be a long video. Sorry about that. But what are we going to do? A lot of material. Chapter 8, Alternating Current Circuits. In earlier chapters, we encountered resistors, capacitors, and inductors. We will now study circuits containing all three of these elements. If such a circuit contains no EMF source, the current takes the form of a decaying oscillation in the case of small damping. The rate of decay is described by the Q factor. If we add on a sinusoidally oscillating EMF source, then the current will reach a steady state with the same frequency of oscillation as the EMF source. However, in general, there will be a phase difference between the current and the EMF. This phase, along with the amplitude of the current, can be determined by three methods. The first method is to guess a sinusoidal solution to the differential equation representing the Kirchhoff loop equation. The second is to guess a complex exponential solution and then take the real part to obtain the actual current. The third is to use complex voltages, currents, and impedances. These complex impedances can be combined via the same series and parallel rules that work for resistors. As we will see, the third method is essentially the same as the second method, but with better bookkeeping. This makes it far more tractable in the case of complicated circuits. Finally, we derive an expression for the power dissipated by a circuit, which reduces to the familiar V squared on R result if the circuit is purely resistive. And off we go. A resonant circuit. It's also called a tank circuit, I think. I'm not sure if they mentioned that here. I'm not sure. On we go. Alternating current. RL circuit. L is, of course, for inductance. RLC circuit. Resonance. Width of the I-O omega curve. The Q factor of the circuit in the above example. All right. Complex exponential solutions, alternating current networks, admittance and impedance, power and energy in alternating current circuits, applications. The resonance of electrical circuits has numerous applications in the modern world. Our lives wouldn't be the same without it. Any wireless communication, from radios to cell phones to computers to GPS systems, is made possible by resonance. If you have a radio sitting on your desk, it is being bombarded by electromagnetic waves, discussed in Chapter 9, with all sorts of frequencies. If you want to pick out a particular frequency emitted by a radio station, you can tune your radio to that frequency by adjusting the radio's resonant frequency. This is normally done by adjusting the capacitance of the internal circuit by using varactors, diodes whose capacitance can be controlled by an applied voltage. Assuming that the resistance of the circuit is small, two things will happen when the resonant frequency matches the frequency of the radio station. There will be a large oscillation in the circuit at the radio station's frequency, and there will also be a negligible oscillation in all the other frequencies that are bombarding the radio. A high Q value of the circuit leads to both of these effects due to the fact that the height of the peak in figure 8.11 is proportional to Q, as you can show, and that the width is proportional to 1 on Q. The oscillation in the circuit can then be demodulated, to the AM/FM discussion in section 9.8, and amplified and sent to the speakers, creating the sound that you hear. Resonance provides us with an astonishingly simple and automatic mechanism for finding needles in haystacks. The microwaves in a microwave oven are created by a magnetron. This device consists of a ring-like chamber with a number, often 8, of cavities around the perimeter. These cavities have both a capacitance and an inductance, and also a small resistance, so they act like little LC circuits. Their size is chosen so that the resonant frequency is about 2.5 gigahertz. The charge on the tips of the little LC cavity alternates in sign around the perimeter of the ring. Charge, and hence energy, is added to the system by emitting electrons from the center of the ring. These electrons are attracted toward the positive tips. If this were the whole story, the effect would be to reduce the charge in the system. But there is a clever way of reversing the effect by applying an appropriate magnetic field. The paths of the electrons can be bent by just the right amount to make them hit the negative tips. Charge is therefore added to the system instead of subtracted. The microwave radiation can be extracted by, say, inducing a current in small coils contained in the LC cavities. The electricity that comes out of your wall socket is alternating current, AC, as opposed to direct current, DC. The RMS voltage in North America is 120 volts and the frequency is 60 Hz. In Europe, the values are 230 volts and 50 Hz respectively. The fundamental reason we use AC instead of DC is that in the case of AC, it is easy to increase or decrease the voltage via transformer. This is critical for the purposes of transmitting power over long distances, because for a given power, P equals IV supplied by a power plant, a large V implies small I, which in turn implies a small I squared R power loss in the long transmission lines. It is much more difficult to change the voltage in the case of DC. This was the deciding factor during the War of Currents in 1880, when AC and DC power were battling for dominance. Because DC power had to be shipped at the same low voltage at which it was used, DC power plants needed to be located within a few miles of the load. This had obvious disadvantages. Cities would need to contain many power plants, and conversely, a dam located far from a populated area would be useless. However, modern developments have made the conversion of DC voltages easier, so high voltage direct current HVDC power transmission is used in some instances. For both AC and DC, the long-haul voltages are on the order of a few hundred kilovolts. The War of Currents pitted, among many other people, Thomas Edison on the DC side against Nikola Tesla on the AC side. Most of the electricity produced in power plants is three-phase. That is, there are 3 separate wires carrying voltages that are 120 degrees out of phase. This can be achieved, for example, by having 3 loops of wire in figure 7.13 instead of just the one shown. There are various advantages to three-phase power, one of which is that it delivers a more steady power compared with single phase, which has 2 moments during each cycle when the voltage is 0. However, this is mainly relevant for large machinery. Most households are connected to only one of the phases or between 2 of them in the power grid. The AC delivered to your home works fine for many electrical devices. For example, a toaster and an incandescent light bulb require only the generation of I²R power, which is created by either AC or DC. But many other devices require DC because the direction of the current in the electronic circuit matters. A power adapter converts AC to DC while generally also lowering the voltage. The voltage is lowered by a transformer, and then the conversion to DC is accomplished by a bridge rectifier, which consists of a combination of 4 diodes that lets the current flow in only one direction. Additionally, a capacitor helps smooth out the DC voltage by storing charge and then releasing it when the voltage would otherwise dip. As mentioned in section 3.9, it is advantageous to perform power factor correction on the AC electrical power grid. The larger the imaginary part of an impedance, say an electrical motor, the larger the phase angle phi, and hence the smaller the cos phi factor in equation 885, which is known as the power factor. I think this has to do with impedance matching, doesn't it? At first glance, this doesn't seem to present a problem because the unused power simply sloshes back and forth between the power station and the motor. However, for a given amount of net power consumed, a smaller power factor means that the current I will need to be larger. This in turn means that there will be a larger I²R power losses in the generally long transmission lines. For this reason, industries are usually charged a higher rate if their power factor is below 95%. In an inductive circuit, for example, a motor with its many windings, the power factor can be increased by adding capacitance to the circuit because this will reduce the magnitude of the imaginary part of the impedance. Chapter summary. The loop equation for the series RLC circuit with no EMF source yields a linear differential equation involving 3 terms, one for each element. In the underdamped case, the solution for the voltage across the capacitor is given, where this is given. The solutions for the overdamped and critically damped cases take other forms. The quality factor of a circuit is given by omega times the energy stored divided by the average power dissipated. There you go. That's how you calculate Q. If we add to the series RLC circuit a sinusoidal EMF source, then the solution for the current is given. This is the steady state solution that survives after the transient solution from section 8.1 has decayed away. I0 is maximum when omega equals the resonant frequency. Omega 0 equals 1 on the square root of LC. The width of I01 omega curve around the resonance peak is on the order of omega 0 on Q. The series RLC circuit can also be solved by replacing the epsilon 0 cos omega t term in the Kirchhoff differential equation with epsilon o e to the power I omega t, and then guessing an exponential solution of the form I bar t equals, I don't know what that is. The actual current IT is obtained by taking the real part. In alternating current networks, currents and voltages can be represented by complex numbers. The real part of the complex number is an actual current or voltage. The complex current and voltage are related to each other via the complex admittance or impedance. The admittances and impedances for the 3 circuit elements RLC are given in table 8.1. Where's table 8.1? I don't know. Admittances add in parallel and impedances add in series. We have presented 3 different methods for solving alternating current networks. See the summary at the end of section 8.5. The average power delivered to a circuit is P equals this, which is basically RMS voltage times the RMS current times cos phi, where RMS values are 1 on root 2 times the peak values. This reduces to this in the case of a single resistor. Right. Chapter 9, Maxwell's equations and electromagnetic waves. In the course of our study of electromagnetism, we have been gradually putting together the pieces of the puzzle of Maxwell's equations. In this chapter, we find the final piece known as the displacement current. We do this by exposing a contradiction in our present theory and then resolving it. Once we write down the full set of Maxwell's equations, we quickly discover that in vacuum they lead to wave solutions with a set of specific properties. These waves are light waves, and unlike other waves you are familiar with, they require no medium to support their propagation. Traveling electromagnetic waves carry energy, and more generally, the Poynting vector describes the energy flowing in an arbitrary electromagnetic field. Standing electromagnetic waves, which are the superposition of traveling waves, carry no net energy. By examining how the I'm going to read that again. That sounds really fascinating. All right, let's just read this whole paragraph again. In the course of our study of electromagnetism, we have been gradually putting together the pieces of the puzzle of Maxwell's equations. In this chapter, we find the final piece known as the displacement current. We do this by exposing a contradiction in our present theory and then resolving it. Once we write down the full set of Maxwell's equations, we quickly discover that in vacuum, they lead to wave solutions with a set of specific properties. These waves are light waves, and unlike other waves you are familiar with, they require no medium to support their propagation. Traveling electromagnetic waves carry energy. And more generally, the Poynting vector describes the energy flow in an arbitrary electromagnetic field. Standing electromagnetic waves, which are the superposition of traveling waves, carry no net energy. By examining how the electric and magnetic fields transform between frames, we find that a light wave in one frame looks like a light wave in any other frame. (9.1) Something is missing. 9.2 The displacement current. 9.3 Maxwell's equations. An electromagnetic wave. Other waveforms. Superposition of waves. Energy transport by electromagnetic waves. Power density. The Poynting vector. How a wave looks in a different frame. Applications. The power density of sunlight when it reaches the Earth, or rather the top of the atmosphere, is about 1,360 watts per square meter on average. You can show that this implies that the total power output of the sun is about 4 times 10 to the power of 26 watts. Wow. If the power in 1 square kilometer of sunlight were converted to electricity at 15% efficiency, the result would be 200 megawatts. However, assuming that the sun is shining for only 6 hours per day on average, this would yield an average of 50 megawatts. Effects of atmospheric absorption and latitude would further reduce the result somewhat. There would still be enough electrical power for a city of 25,000 people. The cosmic microwave background radiation, CMB, see exercise 925, was discovered by Penzias and Wilson in 1965. This radiation is left over from the Big Bang and fills all of space. About 300,000 years after the Big Bang, the universe became transparent to photons. shortly after the hot plasma of electrons and ions cooled to the point where stable atoms could form. The CMB photons have been traveling freely ever since. The wavelength was shorter back then, but it has been continually expanding along with the expansion of the universe. The radiation consists of a distribution of wavelengths, but the peak is around 2 millimeters. It looks nearly the same in all directions, but its slight antistropies yield information about what the early universe looked like. Comets generally have two kinds of tails. The dust tail consists of dust and is pushed away from the comet by the radiation pressure from the sunlight. The sunlight carries energy, so it also carries momentum. See problem 9.11. The dust drifts relatively slowly away from the comet, so this results in the tail curving and drifting behind the comet. The ion tail consists of ions that are blown away from the comet by the sun's solar wind, consisting of charged particles. These ions move very quickly away from the comet, so the ion tail always points essentially radially away from the sun, independent of the comet's location around the sun. Radio frequency identification, RFID, tags have many uses. Anti-theft tags, inventory tracking, toll booth transponders, chip timing in road races, library books, and so on. Although some RFID tags contain their own power source, most called passive RFID do not. They are powered by resonance inductive coupling. A small coil and capacitor in the tag constitute an LC circuit with a particular resonant frequency. A reader transmits a radio wave with this frequency, and the changing magnetic field in this wave induces a current in the tag circuit. This powers a small microchip, which then transmits a specific identification message back to the reader. Cell phones, radios, and many other communication devices make use of electromagnetic waves in the radio frequency part of the spectrum, usually from about 1 megahertz to a few gigahertz. A pure sinusoidal wave at a given frequency contains minimal information. So if we want to transmit useful information, we must modify the wave in some manner. The two simplest ways of modifying the wave are amplitude modulation and frequency modulation. In the case of AM, the carrier wave with a frequency in the 1 megahertz range has its amplitude modulated by the sound wave with a much smaller frequency in the 1 kilohertz range. That is being sent. The larger the value of the sound wave at a given instant, the larger the amplitude of the transmitted wave. The sound wave is, in some sense, the envelope of the transmitted that doesn't make sense. The sound wave is in some sense the envelope of the transmitted wave. The receiver is able to extract the amplitude information and can then reconstruct the original sound wave. I think it means that it's not the sound wave is the envelope. A plot of the amplitude of the transmitted wave as a function of time is effectively the plot of the original sound wave as a function of time. In the case of FM, the carrier wave with a frequency of around 100 megahertz, as you knew from your FM radio dial, has its frequency modulated by the sound wave that is being sent. The larger the value of the sound wave at a given instant, the more the carrier wave frequency shifts relative to a particular value. The receiver is able to extract the frequency information and can then reconstruct the original sound wave. A plot of the frequency as a function of time is effectively a plot of the original sound wave as a function of time. Note that this frequency is well defined, because even if a time interval is fairly short on the time scale of the sound wave, a very large number of the carrier wave oscillations still fit into it. One method of extracting the frequency information is called slope detection. In this method, the resonant frequency of the receiver is chosen to be slightly shifted from that of the carrier wave, so that the span of the carrier wave's frequencies lies on the steep side part of the resonance peak. If the span lies, say, on the left side of the peak, then the response of the receiver's circuit increases approximately linearly as the frequency of the carrier wave increases. So we simply need to measure the amplitude of the current in the circuit, and we will obtain the frequency of the carrier wave up to some factor. The thing that makes all of this possible is resonance, which enables the receiver to respond to a narrow range of frequency and ignore all the others. Chapter summary. Because the divergence of the curl of a vector is identically zero, the differential form of Ampere's law, curl B equals mu 0j, implies that div j is identically zero. This is inconsistent with the continuity equation, which follows from conservation of charge in situations where rho changes with time. Therefore, curl B equals mu 0j cannot be correct. The correct expression has an extra term on the right hand side. With this term, div j correctly equals this as given. The quantity of the permittivity of free space is called the blah 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 is called the displacement current. This is the last piece of the puzzle, and we can now write down the complete set of Maxwell's equations. 1, 2, 3, 4. These are, respectively, Faraday's law, Ampere's law with the addition of the displacement current, Gauss's law, and the statement that there are no magnetic monopoles. A possible form of traveling electromagnetic wave is given. In general, we can produce a traveling wave by replacing this term with any function, provided that this holds. E and B are perpendicular to each other and also to the direction of propagation. A standing wave is formed by adding two waves traveling in opposite directions. In a standing wave, there are, unlike in a traveling wave, positions where E is zero at all times and times when E is zero at positions. Likewise for B. The power density, energy per unit area per unit time, of a sinusoidal electromagnetic wave can be written in various forms. More generally, the Poynting vector gives the power density of an arbitrary electromagnetic field at every point. Using the fact that E and B fields transform according to the Lorentz transformations, we can derive two invariants. These imply that if one frame E and B these imply that if in one frame E and B are perpendicular and E equals CB, then these two relations are also true in any other frame. That is, a light wave in one inertial frame looks like a light wave in any other inertial frame. Chapter 10. Electric fields in matter. In this chapter, we study how electric fields affect and are affected by matter. We concern ourselves with insulators or dielectrics characterized by a dielectric constant. We study the study of electric fields in matter is largely the study of dipoles. We discussed these earlier in chapter 2, but we will derive their properties in more generality here, showing in detail how the multiple expansion comes about. The net dipole moment induced in matter by an electric field can come about in two ways. In some cases, the electric field polarizes the molecules. The atomic polarizability quantifies this effect. In other cases, a molecule has an inherent dipole moment, and the external field serves to align these moments. In any case, a material can be described by a polarization density P. The electric susceptibility gives, up to a factor of the permittivity of free space, the ratio of P to the electric field. The effect on the polarization density is to create a surface charge density on a dielectric material. This explains why the capacitance of a capacitor is increased when it is filled with a dielectric. The surface charge on the dielectric partially cancels the free charge on the capacitor plates. We study this special case of a uniformly polarized sphere, which interestingly has a uniform electric field in its interior. We then extend this result to the case of a dielectric sphere placed in a uniform electric field. By considering separately the free charge and the bound charge, we are led to the electric displacement vector D, whose divergence involves only the free charge, unlike the electric field, whose divergence involves all the charge by Gauss's law. We look at the effects of temperature on the polarization density, how the polarization responds to rapidly changing fields, and how the bound charge affects the curl B Maxwell equation. Finally, we consider an electromagnetic wave in a dielectric. We find that only a slight modification to the vacuum case is needed. And we're away. Dielectrics. The moments of a charge distribution. The potential and field of a dipole. Torque and the force of a dipole in an electric field. Atomic and molecular dipoles, induced dipole moments. Permanent dipole moments. Electric field caused by polarized matter. The field outside matter. The field inside matter. We can now address the field inside polarized matter. It is the internal field. Is the internal field the same in the two systems in figure 1017? Certainly not, because the slab is full of positive nuclei and electrons, with fields on the order of 10 to the 11 volts per meter pointing in one direction here, another direction there. But one thing is the same. The line integral of the field, reckoned over any internal path from A to B, must be phi b minus phi a, which, as we have seen, is the same as phi b prime minus phi a prime, which is equal to sigma t divided by the permittivity of free space, or pt divided by the permittivity of free space. This must be so because the introduction of atomic charges, no matter what their distribution, cannot destroy the conservative property of the electric field expressed in the statement that the integral of EDS is independent of path or curl E0. We know that in figure 1017b, the potential difference between the top and bottom sheets is nearly constant, except near the edges, because of the interior electric field is practically uniform. Therefore, in the central area of our polarized plate, the potential difference between the top and bottom must likewise be constant. In this region, the line integral taken from any point A on top of the slab to any point B on the bottom by any path must always yield the same value. Figure 1018 is a magnified view of the central region of the slab, in which the polarized molecules have been made to look something like H2O molecules, all pointing the same way. We have not attempted to depict the very intense fields that exist between and inside the molecules. The field 10 angstroms away from a water molecule is on the order of 100 megavolts per meter, as you can discover from these equations. All right. Another look at the capacitor. The field of a polarized sphere. A dielectric sphere in a uniform field. The field of a charge in a dielectric medium and Gauss's law. Sticky pages. A microscopic view of the dielectric. Polarization in changing fields. The bound charge current. An electromagnetic wave in a dielectric. Applications. The pollination of flowers by bees is helped by polarization effects. When bees travel through the air, they become positively charged due to Triboelectric effects with the air. Air molecules strip off electrons from the bee when its wings collide with the molecules. When the bee gets close to the pollen on the anther of the flower, the bee's charging polarizes the pollen, which then experiences a dipole attraction toward the bee. The pollen jumps to the bee and lands on the bee's hairs while maintaining zero net charge because the hairs aren't conductive. When the bee then gets close to the stigma of a flower, it induces a negative charge on the stigma. The electric field from the somewhat pointed stigma wins out over the field from the somewhat rounded bee, so the pollen jumps to the stigma. Note the lack of symmetry between the anther and the stigma. The anther gives up the pollen while the stigma attracts it. This lack of symmetry arises mainly from the fact that the stigma has a more conductive path to ground than the anther has, so it can acquire a net negative charge when the bee is near. The stigma's attraction to the pollen is therefore of the monopole-dipole type, whereas the anther's attraction to the pollen is of the smaller dipole-dipole type. The ability of the gecko lizard to stick to a window or a wall upside down on a ceiling, or walk upside down on a ceiling, is due to the van der Waals force. This force is an interaction between dipoles in the gecko's feet and dipoles on the surface. The force falls off rapidly with distance being proportional to 1 on r to the power of 7. Holy cow. Equivalently, the potential energy is proportional to 1 on r to the power of 6. In short, quantum fluctuations create random dipole moments in a given molecule. The resulting field induces a dipole moment in a neighboring molecule. The resulting force on this molecule is then proportional to 1 on r to the power of 7. The key for geckos, therefore, is to make the distance r be as small as possible. They do this by having hundreds of thousands of tiny hairs called setae on their feet, each of which contains hundreds of even tinier hairs called spatula. These spatula are able to penetrate the nooks and crannies on the surface, making the various distances r extremely small. If all of a gecko's spatula are engaged, it could walk on a ceiling with a few hundred pounds strapped to it. The main ingredient in soaps and detergents is a surfactant. This is a molecule in the form of a long chain with a polar end and a non-polar end. The polar end is attracted to the polar water molecules. It is called hydrophilic, whereas the non-polar end isn't. It is called hydrophobic. The non-polar end is instead attracted to other hydrophobic molecules, such as oils and other grime on you or your clothes. More precisely, the hydrophobic ends / molecules aren't actually attracted to each other. Rather, the attraction of all the polar molecules to themselves has the effect of forcing all the hydrophobic ends / molecules into little clumps called micelles. Okay, don't know how to pronounce that word. This gives the appearance of an attraction. The same reasoning leads to the everyday fact that oil and water don't mix. The clumps with the oils and non-polar surfactant ends in the interior and the polar surfactant ends on the surface float around in the water, and you can be eliminated by discarding the water, that is, by rinsing. So your laundry detergent won't work without water. The average dipole moment of a water molecule is what allows a microwave oven to heat your food. The alternating electric field of the microwave radiation created by a magnetron, see section 8.7, causes the water dipoles to rotate back and forth. This jiggling of the molecules causes them to bump into each other, which results in the thermal energy that you observe. The specific microwave frequency that is used, usually about 2.5 gigahertz, which corresponds to a wavelength of about 12 centimeters, has nothing to do with the resonant vibrational frequency of a free water molecule in vapor, which is about 20 gigahertz. There isn't anything special about the 12 centimeter wavelength, although if it were much shorter, the waves wouldn't penetrate the food as well. The water molecules in ice can't rotate as easily, so that's why it takes a while to defrost frozen food. You can't just crank up the power, because if one part of the food thaws first, then it will absorb energy much faster than the remaining frozen part. You will then end up with, for example, thoroughly cooked meat right next to frozen meat. The defrost cycle in a microwave oven functions by simply shutting off for periods of time, allowing the heat to diffuse. When some materials such as quartz are put under stress and bent, a voltage difference arises between different parts. This is known as the piezoelectric effect. Conversely, if a voltage difference is applied to different parts, the material will bend. What happens is that the molecules are stretched or squashed, and for certain configurations, this results in the molecules acquiring a dipole moment. The material therefore behaves like a polarized dielectric. There are net surface charges, so the result is effectively a capacitor with a voltage difference between the plates. The piezoelectric property of quartz allows your wristwatch to keep time. A tiny quartz crystal, which is the analog of the pendulum in a pendulum clock, is cut so that it vibrates with a specific resonant frequency, usually 2 to the power of 15 equals 32,768 Hz. This power of 2 makes it easy for a chain of frequency dividers to generate the desired 1 Hz frequency. Via the piezoelectric effect, an electric signal with this 32,768 Hz frequency is sent to a circuit. The circuit then amplifies the signal and sends it back to the crystal, providing the necessary driving force to keep the resonant oscillation going. Quartz has a very high Q value, so only a tiny amount of input energy is needed. That is why the battery can last so long. The oscillations are initially produced by the random AC noise in the circuit. This AC noise contains at least a little bit of the resonant frequency, which the crystal responds to. Wow. I think it's cool how you can kick off a resonator by just getting some noise out of the environment. I think I've seen it before where the resonating wouldn't start all the time. I forget the details of that. Okay, chapter summary. If a capacitor is filled with a dielectric, an insulator, the capacitance increases by a factor K. Is that K or is it kappa? I don't know. What does kappa look like? Yeah, kappa looks like K. Probably kappa. Let's say it's kappa. If a capacitor is filled with a dielectric, an insulator, the capacitance increases by a factor kappa, known as the dielectric constant. This is a consequence of the fact that the polarization of the molecules in the dielectric causes layers of charge to form near the capacitor plates, partially cancelling the free charge. The potential due to a charge distribution can be written as the sum of terms with increasing powers of 1 on R. The coefficients of these terms are called moments. A net charge has a monopole moment. Two opposite monopoles create a dipole. Two opposite dipoles create a quadrupole, and so on. The potential of and field due to a dipole are given as this. The torque on an electric dipole is given as N equals P times E. The force is Fx equals P. What did we call that? I forget what that was called. And likewise for Y and Z components. An external electric field will cause an atom to become polarized. The atomic polarizability alpha is defined as this, given the quantity of this expression should be which has the dimensions of volume. Is also commonly called the atomic polarizability. In order of magnitude, this expression equals an atomic volume. Some molecules have a permanent dipole moment. The moment exists even in the absence of an external electric field. These are called polar molecules. An external electric field causes the dipoles to align, at least partially, which leads to an overall polarization of the material. The polarization per unit volume is given as P equals Pn. Uniformly polarized matter is equivalent to a surface charge density of sigma equals P, or sigma equals P cos theta if the surface is tiled with respect to the direction of P. When we talk about the electric field inside matter, we mean the spatial average. Inside a uniformly polarized slab, the average is minus P on epsilon 0, which is the permittivity of free space, whatever that is. The electric susceptibility, okay, that is not X. What do we call that? It's not jumping out at me. Oh yeah, it's lowercase chi. All right. The field inside a uniformly polarized sphere is minus P on 3 epsilon 0 if a dielectric sphere is placed in a uniform electric field E0, the resulting polarization is uniform and is given as this. For any material, this expression holds. Combining this, I should say this equation holds. Combining this with Gauss's law, we get this. D is known as the electric displacement vector. If additionally we are dealing with a linear dielectric, then these equations hold. If an external electric field is applied to a dielectric containing polar molecules, the polarizations tend to align with the field, but thermal energy generally prevents the alignment from being large. The susceptibility is given roughly by this equation. In a rapidly changing electric field, the induced polarization of atoms and molecules can keep up with the field at high frequency. However, the polarization arising from polar molecules cannot, because it is much more difficult to rotate a molecule as a whole than simply stretch it. The bound charge current density satisfies J bound equals dP dt. This represents a true current, but when writing the curl B Maxwell equation, it is often convenient to separate this current from the free charge current. An electromagnetic wave in a dielectric travels with speed V equals 1 on the square root of mu 0 epsilon. This is slower than the speed of light in a vacuum by the factor of 1 on the square root of kappa. The index of refraction equals the inverse of this, n equals the square root of kappa. The E and B fields are still perpendicular to each other and to the direction of travel. Their amplitudes are related by this expression or equation. It's a long video again. I always feel a bit guilty when I put out these long videos. All right, this is the chapter 11, magnetic fields in matter. Magnetic fields in matter are a bit more involved than electric fields in matter. Okay, magnetic fields in matter are a bit more involved than electric fields in matter. Our main goal in this chapter is to understand the three types of magnetic materials: diamagnetic materials, which are weakly repelled by a solenoid; paramagnetic materials, which are somewhat strongly attracted; and ferromagnetic materials, which are very strongly attracted. As was the case in chapter 10, we will need to understand dipoles. The far field of a magnetic dipole has the same form as that of an electric dipole, with the magnetic dipole moment replacing the electric dipole moment. However, the near fields are fundamentally different due to the absence of magnetic charge. We will find that diamagnetism is due to the fact that an applied magnetic field causes the magnetic dipole moment arising from the orbital motion of electrons in atoms to pick up a contribution pointing opposite to the applied field. In contrast, in the case of paramagnetism, the spin dipole moment is the relevant one, and it picks up a contribution pointing in the same direction as the applied field. Ferromagnetism is similar to paramagnetism, although a certain quantum phenomenon makes the overall effect much larger. The ferromagnetic dipole moment can exist in the absence of an external magnetic field. Magnetized materials can be described by the magnetization M, the curl of which gives the bound currents which arise from both orbital motion and spin, by considering separately the free and bound currents, which we are led to by considering separately the free and bound currents, we are led to the field H, also called the magnetic field, whose curl involves only the free current, unlike the magnetic field B, whose curl involves all the current by Ampere's law. All right, how various substances respond to a magnetic field. The absence of magnetic charge, charge in air quotes there. The field of a current loop. The force on a dipole in an The force on a dipole in an external field. Electric currents in atoms. Electron spin and magnetic moment. Magnetic susceptibility. The magnetic field caused by magnetized matter. The field of a permanent magnet. Free currents in the field H. Ferromagnetism. Applications. Lodestone is magnetite, which is a type of iron oxide that has been magnetized. Most magnetite isn't lodestone. The Earth's magnetic field is too weak to create the observed magnetization, and additionally, a particular crystal structure in the magnetite is needed. A much stronger field is required, and this is the field produced by the brief but large electric current in a lightning strike. So without lightning, there would be no magnetic compasses, and the explorers throughout history would have had a much more difficult time. Red pigments in paint often contain iron oxide grains. When the paint is wet, the grains' magnetic dipole moments are free to rotate and align themselves with the Earth's magnetic field, but when the paint dries, they are locked in place. The direction of the dipole moments in a painting therefore gives the direction of the Earth's magnetic field at the time the painting was made. By studying painting whose positions are fixed, such as murals, we can gather information on how the Earth's magnetic field has changed over time, assuming that the creation dates are known. This doesn't work with frame paintings that have been moved around, or with murals that have undergone restoration. Conversely, knowing the direction of the dipoles in a given painting can help determine the creation date. This can be very useful for archaeological purposes. A common application of ferromagnetic materials is the magnification of the magnetic field from a coil of wire. If a coil is wrapped around a ferromagnetic core, usually iron-based, the coil's magnetic field causes the spins in the core material to align with the field, thereby producing a much larger field than the coil would produce by itself. This magnification factor, which is just the relative permeability of mu1, mu0, depends on various things, but for ferromagnetic materials it can be 100 or 1000 or even larger. This magnification effect is used by the electromagnets in relays, circuit breakers, junkyard magnets, and many other devices. See section 610. Many data storage devices, from cassette tapes to computer hard disks to credit cards, rely on the existence of ferromagnetic materials. There are many other types of storage devices too. For example, CDs and DVDs operate by reflecting laser light off any tiny pits in a plastic disc coated with aluminium. And flash memory makes use of a special kind of transistor. A cassette tape, RIP, there we go. A cassette tape was the dominant format for music recording in the 1980s. The cassette consisted of a long plastic tape coated with iron oxide, wound around two small reels. The read-write head is a tiny electromagnet. In the writing or recording mode, a current passes through the coil of the electromagnet, producing a magnetic field that aligns the magnetic dipoles on the tape as it moves past. The tape therefore encodes the information in the current in the original signal. There's a note here. The process is complicated due to hysteresis. The magnetization tends to keep its original value and doesn't respond linearly to the applied magnetic field. This is remedied by adding a bias signal to the original signal. The purpose of the bias signal, whose frequency is high, usually around 100 kilohertz, is basically to average out the positive and negative effects of the hysteresis. Conversely, in the reading or playback mode, the magnetic field of the dipoles in the tape induces a current in the electromagnetic as the magnetic domains in the tape move past. This induced current contains the same information that was on the tape. It can then be amplified and sent to a speaker. Computer hard disks operate under the same general principle as a cassette tape, although there are some differences. Instead of a long tape, the hard disk, as the name suggests, takes the form of a disk on which the magnetic data is encoded in very narrow circular tracks. The magnetic domains are much smaller and the average linear speed relative to the read-write head is much larger. The information at a given location on a disk can be accessed much more quickly than on a linear tape because there is no need to run through the tape to gain access to a given point. Another important difference is that the cassette tape is an analog device, whereas the hard disk is a digital one. That is, as the current in the cassette's write head electromagnet changes smoothly, the induced magnetization of the tape also changes smoothly, and this smoothly varying function contains the desired information. But in a hard disk, the magnetization is all or nothing. The write head electromagnetic either does nothing or completely saturates a magnetic domain. The abrupt changes, or lack thereof, in the magnetization are what is detected by the read head. So the information, I don't know if that's actually quite true. It might actually not be. So I don't know. So the information that comes out is just a string of yeses or nos, that is ones or zeros. In modern computers, the reading is done with a separate magnetoresistive head whose resistance depends on the magnetic field from the disk. This type of head is better able to read the tiny magnetic features on the disk. As incredibly useful as magnetic data storage is, beware that it isn't permanent. Hard disk data can degrade on the order of 10 years. If you really want your data to last, you can use CDs that are made with a layer of gold. These are designed to last 300 years, although the supporting hardware will certainly be replaced long before then. As discussed in exercise 1125, magnetic bacteria contain crystals of iron, often in the form of magnetite, that keep the bacteria aligned with the Earth's magnetic field. The alignment is passive, that is, it would work even if the bacterium were dead. The point of the alignment is not to indicate which way is north, but rather which way is down. Except near the magnetic equator, the Earth's magnetic field is inclined vertically. In the simplest scenario, the bacteria follow the downward field lines to the oxygen-deprived regions, which they like in the mud. However, other mechanisms allow them also to seek out oxygen-deprived layers of water higher up. The orientation of the magnetization of the crystals is opposite in bacteria in the northern and southern hemispheres, so they all do indeed swim downward. If a bacterium is transported to the other hemisphere, it will swim upward. Near the magnetic equator, there are roughly equal numbers of each type, and presumably another navigation mechanism takes over. Many other creatures, such as homing pigeons, sea turtles, and rainbow trout, also use the Earth's magnetic field to navigate. The exact mechanism isn't known, but with pigeons, for example, the beak most likely contains tiny crystals of magnetite that transmit a signal to the brain. The mechanism differs from the one in bacteria in that it is active, that is, a signal needs to be sent, rather than passive. In bacteria, the torque on the magnetic crystals simply rotates the bacteria. Also, for pigeons, the purpose of the magnetite is to indicate which way is north or south, and not which way is down, as in the case of bacteria. A bacterium wants to make a beeline along a magnetic field line to the mud. whereas a pigeon has no great desire to make a beeline for the ground. A ferrofluid consists of tiny, on the order of a nanometer, ferromagnetic particles suspended in fluid. A surfactant, discussed in section 1016, keeps the particles evenly distributed in the fluid so that they don't all clump together in the presence of a magnetic field. When a magnetic field is applied, a ferrofluid can take on bizarre shapes, with spikes and valleys brought about by the complicated balancing of magnetic, gravitational, and surface tension. Aside from making cool shapes, ferrofluids have many useful applications in magnetic resonance imaging, as seals in devices with rotating parts, and as means of heat transfer. The ability to transfer heat efficiently is due to the temperature dependence of the magnetic susceptibility. In a speaker, for example, heat is generated near the voice coil, and the hotter ferrofluid with a smaller magnetization than the cooler ferrofluid will experience a smaller magnetic force and can therefore be displaced towards the heatsink. Magnetoheliological fluids are similar to ferrofluids, except that the magnetic particles are larger. When a magnetic field is applied, the particles tend to line up along the field lines, which increases the viscosity in the orthogonal direction. One application is in shock absorbers, where an electromagnet constantly adjusts the stiffness of the fluid depending on the instantaneous road condition. If you hold one permanent magnet above another, you can pick up the bottom one. So the magnetic force from the top magnet does work on the bottom magnet. However, isn't it the case that magnetic forces do no work because the QV times B Lorentz force is always perpendicular to the velocity v? Actually, no. Magnetic forces can do work in some cases. More precisely, the no magnetic work conclusion holds only if the force is governed by the QV times B Lorentz force, which applies to point charges moving through space. This force law has nothing to do with the force on a magnetic dipole arising from a quantum mechanical spin, which cannot be viewed as a tiny current loop. The force on a dipole is instead given as this. Although we motivated this force law in section 11.4 by considering a current loop, it can in fact be derived from fundamental physical principles, relativity, quantum mechanics, and a few other things, with no reference to moving charges or the Lorentz force. This expressed force has a potential energy associated with it, and the change in this potential energy equals the work done on the dipole. If you picked up an actual current ring by holding another current ring above it, then as the bottom ring moved upward, you can show that the current in it would decrease, which the spin of an electron can't do. A battery or something would be needed to maintain the current, and this battery would be the agency doing the work, because the no magnetic work conclusion would hold in this case. See problem 7.2 for a related setup and a detailed discussion of why the magnetic Lorentz force ends up doing zero net work on moving charges. Most permanent magnets are made of a combination of iron and other elements such as nickel, cobalt, and oxygen. But in recent years, permanent magnets made of rare earth elements such as neodymium and samarium, combined with other more common elements, have come into wide usage. Rare earth magnets are generally a bit stronger than iron-based ones. The fields are often in the 1 to 1.5 Tesla range, whereas the field of an iron magnet is usually less than 0.5 Tesla, although it can reach 1 Tesla for some types. Additionally, the crystal structure of a rare earth magnet is highly anisotropic. As discussed in the answer to question 2 in section 11.11, this means that it is difficult to change the direction of the individual magnetic dipole moments. It is therefore difficult to demagnetize a rare earth magnet. Rare earth magnets have replaced standard iron magnets in many electronic devices. All right, chapter summary. There are three types of magnetism. One, diamagnetism arises from the orbital angular momentum of electrons. A diamagnetic moment points antiparallel to the external magnetic field. Two, paramagnetism arises from the spin angular momentum of electrons. A paramagnetic moment points parallel to the external magnetic field in an average sense. And three, ferromagnetism also arises from the spin of angular momentum of electrons, but the interactions involved can be explained only with quantum mechanics. A ferromagnetic moment can exist in the absence of an external magnetic field. The force on a diamagnetic material points in the direction of decreasing magnetic field strength, while the force on a paramagnetic material points in the direction of increasing magnetic field strength. The force on a ferromagnetic material can point either way, but in a field strong enough to wash out any initial magnetization that may have existed, the force points in the direction of increasing magnetic field strength. Unlike electric fields, magnetic fields are caused by currents, not poles. The absence of magnetic poles can be stated as div B equals 0, which is the fourth of our Faraday's Maxwell's equations. Maxwell's equations, the fourth one, as I recall. The magnetic moment of a current loop is m equals IA. The vector potential due to the loop can be written as this, and the magnetic dipole field in spherical coordinates is given as this. The force on a magnetic dipole is this. This takes a different form compared with the force on an electric dipole. The magnetic moment due to the orbital motion of an electron is m equals this, where L is the orbital angular momentum. The diamagnetic moment induced in external field B is m equals this. Electrons also contain spin, angular momentum, and a spin dipole moment. Paramagnetism arises from the partial alignment of the spins. The torque on a dipole moment is this. In many cases, the diamagnetic and paramagnetic dipole magnetization M are proportional to the applied external field B. The magnetic susceptibility can be defined as M equals this through a different definition, although a different definition in terms of H, see below, is the conventional one. The paramagnetic susceptibility is given as this. The magnetic field due to a uniformly magnetized slab is equivalent both inside and outside to the magnetic field due to a current on the side surface with density as given. If the magnetization is not constant, then we more generally have J equals curl M. The magnetic field H is defined as this. This satisfies these equations. If M is proportional to B, then the accepted definition of the magnetic susceptibility is this. The magnetic permeability is defined as this. Like paramagnetism, ferromagnetism arises from the spin angular momentum of electrons, but in a more inherently quantum mechanical way that allows magnetization to exist even in the absence of an external magnetic field. A ferromagnetic material is divided into different domains where the spins are aligned. Increasing the external magnetic field can shift the boundaries of these domains. However, this process is not exactly reversible, an effect called hysteresis. And then we're off onto our problems and our exercises. Chapter 12, Solutions to the Problems. This is the end, my friend. We made it to chapter 12. This is where it gives you the solutions to the problems. There's heaps of problems in here. And the solutions are given, which is great. We're going to have a flip through the appendices, and then we're going to call it a wrap. I would love to spend the time to learn all of this in great depth, but I'm not going to come back to it until my mathematics is a bit better than it is. So that I can engage with the material, and that's going to take years. Anyway, here we are. Appendix A, differences between SI and Gaussian units. In this appendix, we discuss the difference between SI and Gaussian systems of units. First, we will look at the units in each system, and then we will talk about the clear and not so clear ways in which they differ. SI units. Consider the SI system, which is, hang on. Consider the SI system, which is the one we use in this book. The four main SI units that we deal with are the meter, the kilogram, the second, and the coulomb. Oh, okay. I didn't know the coulomb was a fundamental unit, but perhaps it is. Oh, there we go. The coulomb actually isn't a fundamental SI unit. It is defined in terms of the ampere, which is a measure of current charge per time. The coulomb is a derived unit defined to be 1 ampere second. The reason why the ampere and not the coulomb is the fundamental unit involving charge is one of historical practicality. It is relatively easy to measure current by a galvanometer, see section 7.1. More crudely, a current can be determined by measuring the magnetic force that two pieces of current carrying wire in a circuit exert on each other, see figure 6.4. Once we determine the current that flows into an object during a given time, we can then determine the charge on the object. On the other hand, although it is possible to measure charge directly via the force that two equally charged objects exert on each other, imagine two balls hanging from strings repelling each other as in exercise 136, I can't say two balls hanging without chuckling. Sorry. The setup is a bit cumbersome. Furthermore, it tells us only what the product of the charges is in the event that they aren't equal. The point is that it is easy to measure current by hooking up an ammeter, the main component of which is a galvanometer, to a circuit. There's a footnote here. If we know the capacitance of an object, then we can easily measure the charge on it by measuring the voltage with a voltmeter. But the main component of a voltmeter is again a galvanometer, so the process still reduces to measuring a current. The exact definition of an ampere is I'm not sure about this, by the way. I think an analog meter and a digital meter, that they actually work differently, and one measures voltage and the other one measures current, but I don't know a whole lot about that. I just have a feeling. I'm not sure. The exact definition of an ampere is if two parallel wires carrying equal currents are separated by 1 meter, and if the force per meter on one wire due to the entirety of the other wire is 2 times 10 to the minus 7 newtons, then the current in each wire is 1 ampere. The power of 10 here is an arbitrary historical artifact and is the factor of 2. This force is quite small, but by decreasing the separation, the effect can be measured accurately enough with this setup shown in figure 6.4. Having defined the ampere in this manner, and then having defined the coulomb as 1 ampere second, which happens to correspond to the negative of the charge of about 2.64 times 10 to the power of 11 electrons, which is just a staggeringly large amount of electrons. A reasonable thing to do, at least in theory, is to find the force between the two 1 coulomb charges located, say, 1 meter apart. Since the value of 1 coulomb has been fixed by the definition of the ampere, this force takes on a particular value. We are not free to adjust it by tweaking any definitions. It happens to be about 9 times 10 to the power of 9 newtons, a seemingly arbitrary number, but in fact related to the speed of light. It has the numerical value of c squared on 10 to the power of 7. We see why in section 6.1. This rather large number, therefore, appears out in front of Coulomb's law. We could label this constant with one letter, such as K, but for various reasons it is labeled as 1/4 pi epsilon 0, where with epsilon 0 because 8.85 times 10 to the minus 12 coulombs squared per second squared per kilogram per cubic meter. These units are what are needed to make the right-hand side of Coulomb's law have units of newtons. In terms of the fundamental ampere unit, the units of the permittivity of free space, area A squared is amperes squared times second to the power of 4 per kilogram per cubic meter. Holy cow. The upshot of all this is that because we made the choice to define current via the Lorentz force, specifically the magnetic part of the Lorentz force, between two wires carrying current I, the Coulomb force between two objects of charge Q ends up being a number that we just have to accept. We can make the prefactor be a nice simple number in either one of these force laws, but not both. There's a note here, the Biot-Savart law, which allows us to calculate the magnetic field that appears in the Lorentz force, contains what appears to be a messy prefactor, namely mu0 on 4 pi. But since mu0 is defined to be exactly this, 4 pi times 10 to the negative 7 kilograms per meter per coulomb squared, this factor takes on the simple value of 10 to the minus 7 kilogram meters per coulomb squared. The SI system gives preference to the Lorentz force due to the historical matters of practicality mentioned above. It turns out that there are actually 7 fundamental units in the SI system. They are listed in table A1. The candela isn't relevant to our study of electromagnetism, and the mole and the Kelvin come up only occasionally. So for our purposes, the SI system consists of essentially just the first 4 units. There's our table of SI base units: length, mass, time, and electric current. Then we've got thermodynamic temperature, amount of substance, and luminous intensity. Cool. Gaussian units. What do the units look like in a Gaussian system? As with SI system, the last 3 of the above units, or the analogues, rarely come up, so we will ignore them. What was that? As with the SI system, the last 3 of the above units or the analogues rarely come up, so we will ignore them. Oh, okay, cool. We're not going to talk about the other ones in the Gaussian system. Fine. The first 2 units are the centimeter and gram. These differ from the SI unit simply by a few powers of 10, so it's easy to convert from one system to the other. The third unit, the second, is the same in both systems. The fourth unit, that of charge, is where the 2 systems fundamentally diverge. The Gaussian unit of charge is the ESU, short for electrostatic unit. ESU, electrostatic unit. It's a charge on an electron, isn't it? Which isn't related to the Coulomb by a simple power of 10. The reason for this non-simple relation is that the Coulomb and the ESU are defined in different ways. The Coulomb is a derivative unit of the ampere, which is defined via the Lorentz force, as we saw above, whereas the ESU is defined via the Coulomb force. In particular, it is defined so that Coulomb's law, which is given, takes on a very simple form with k equals 1. The price to pay for this simple form of the Coulomb force is not a simple form of the Lorentz force between 2 current-carrying wires, although it isn't so bad. Like the Coulomb force in SI units, it just involves a factor of c squared. See equation 616. This is the opposite of the situation with the SI system, where the Lorentz force is the nice one. Again, in each system we are free to define things so that one, but not both, of the Lorentz force and the Coulomb force takes on a nice form. Main differences between the systems. In section A2, we glossed over what turns out to be the most important difference between SI and Gaussian systems. In the SI system, the constant in Coulomb's law is this, and it has non-trivial dimensions, whereas in the Gaussian system, the constant kg equals 1 is dimensionless. We aren't just being sloppy and forgetting to write the units. K is simply the number 1. I don't understand how a number can not have a dimension. I mean, well, I don't know. Obviously it can. I'm going to make more coffee. Alright, I'm back with the fresh coffee. And yeah, our dimensionless numbers. I mean, I understand pure numbers. It's just a pure number. It's got no dimensions, a number. But in physics, I don't know. Maybe it'll tell us here. Although the first thing that may strike you about the two K constants is the large difference in their numerical values. This difference is fairly inconsequential. It simply changes the numerical size of various quantities. The truly fundamental and critical difference is that KSI has units, whereas KG does not. We could, of course, imagine a system of units where K equals 1 dyne centimeter squared per ESU squared. This definition would parallel the units of KSI, with the only difference being the numerical value. But this is not what the Gaussian system does. The reason why the dimensionlessness of Kg creates such a profound difference between the two systems is that it allows us to solve for the ESU in terms of other Gaussian units. In particular, from looking at the units in Coulomb's law, we can write, using 1 dyne equals 1 gram centimeter per square second, dyne equals dimensionless times ESU squared on centimeter squared goes to ESU equals the square root of g centimeters cubed per square centimeter per square second. No, per square s displacement. The ESU is therefore not a fundamental unit. It can be expressed in terms of the gram, centimeter, and second. In contrast, the SI unit of charge, the Coulomb, cannot be similarly expressed. Since KSI has units of Newton meters squared per Coulomb squared, the coulombs and everything else cancel in Coulomb's law, and we can't solve for C in terms of other units. For our purposes, therefore, the SI system has 4 fundamental units: mass, weight, displacement. No, that's time. S for time. Seconds. Right. Per second squared. Okay, that's confusing. I'm confused. They use S as the variable for displacement, but they use S for the indication of the time, seconds. Anyway, whereas the Gaussian system has only 3. Okay, centimeter, gram, and second. We will talk more about this below, but first let us summarize the 3 main differences between the SI and Gaussian systems. We state them in order of increasing importance. The SI system uses kilograms and meters, whereas the Gaussian system uses grams and centimeters. This is the most trivial of the 3 differences because all it does is introduce some easily dealt with powers of 10. 2. The SI unit of charge, the Coulomb, is defined via the ampere, which in turn is defined in terms of the force between current-carrying wires. The Gaussian unit of charge, the ESU, is defined directly in terms of Coulomb's law. This latter definition is the reason why Coulomb's law takes on a nicer form in Gaussian units. The differences between the two systems now involve more than simple powers of 10. However, although these differences can sometimes be a hassle, they aren't terribly significant. They are just numbers, no different from powers of 10, except a little messier. All of the conversions you might need to use are listed in Appendix C. And 3. In Gaussian units, the K in Coulomb's law is chosen to be dimensionless, whereas in SI units, the K, which involves the permittivity of free space, has units. There's a note here. To draw a more accurate analogy, in SI units, the defining equation for the ampere, from which the Coulomb is derived, contains the dimension full constant μ0 in the force between 2 wires. The result is that the ESU can be expressed in terms of other Gaussian units, whereas the analogous statement is not true for the Coulomb. This is the most important difference between the two systems. 3 units versus 4. Let us now discuss in more detail the issue of the number of units in each system. The Gaussian system has one fewer because the ESU can be expressed in terms of other units via equation A4. This has implications with regard to checking units at the end of the calculation. In short, less information is gained when checking units in the Gaussian system because the charge information is lost when the ESU is written in terms of the other units. Consider the following example. In SI units, the electric field due to a sheet of charge is given in equation 140 as sigma on to epsilon 0. In Gaussian units, the field is 2 pi sigma. Recalling the units of epsilon 0 in equation 1.3, the units of the SI field are kilogram meters per coulomb per square second, or kilogram meters area per yeah. Other A is not area, it's amperes. If you want to write it in terms of amperes, but we use coulombs here to show analogies with ESU. This correctly has dimensions of force per charge. The units of the Gaussian 2 pi sigma field are simply ESU on square centimeters, but since the ESU is given by equation A4, the units are grams to the power of a half. Oh, it's the square root of the gram per centimeter. Gee, that's complicated. These are the true Gaussian units of the electric field when written in terms of fundamental units. Now let's say that two students working in the Gaussian system are given a problem where the task is to find the electric field due to a thin sheet with charge density sigma, mass m and volume v, moving with a non-relativistic speed v. The first student realizes that most of this information is irrelevant and solves the problem correctly, obtaining the answer 2 pi sigma, ignoring relativistic corrections. The second student royally messes things up and obtains an answer of this, since the fundamental Gaussian units are blah blah blah, which is the correct Gaussian units, more generally, blah 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 blah. Okay, there are of course also many ways to obtain incorrect answers in the SI system that just happen by luck to have the correct units. Correctness of the units doesn't guarantee correctness of the answer. But the point is that because the charge information is swept under the rug in Gaussian units, we have at our disposal the information of only 3 fundamental units instead of 4. Compared with the SI system, there is therefore a larger class of incorrect answers in the Gaussian system that have the correct units. Yeah, right. The definition of B. Another difference between the SI and Gaussian system of units is the way in which the magnetic field is defined. In SI units, the Lorentz force, or rather the magnetic part of it, is F equals QV by B, whereas in Gaussian units it is F equals Q on CV times B. This means that whenever a B appears in an SI expression, a B on C appears in the corresponding Gaussian expression, among other possible modifications. Or equivalently, a Gaussian B turns into an SI CB. This difference, however, is a trivial definition one and has nothing to do with the far more important difference discussed above, where the ESU can be expressed in terms of other Gaussian units. In the Gaussian system, E and B have the same dimensions. In the SI system, they do not. The dimensions of E are velocity times the dimensions of B. In this sense, the Gaussian definition of B is more natural because it makes sense for two quantities to have the same dimensions if they are related by a Lorentz transformation, as the E and B fields are. See equation 672 for the SI case and equation 677 for the Gaussian case. After all, the Lorentz transformation tells us that the E and B fields are simply different ways of looking at the same field depending on the frame of reference. However, having CB instead of B in the SI Lorentz transformation can't be so bad because X and T are also related by a Lorentz transformation and they don't have the same dimensions. The direct correspondence is between X and CT. Likewise for P and E, where the direct correspondence is between PC and E. At any rate, This issue stems from the arbitrary choice of whether a factor of C is included in the expression for the Lorentz force. One can easily imagine an SI-type system where charge is a distinct unit in which the Lorentz force takes the form F equals QE plus Q on CV times B, yielding the same dimensions for E and B. Rationalized units. You might wonder why there are factors of 4 pi in the SI versions of Coulomb's law and the Biot-Savart law. See equations 1, 4 and 649. These expressions would certainly look a bit less cluttered without these factors. The reason is that the presence of 4 pi's in these laws leads to the absence of such factors in Maxwell's equations, and for various reasons it is deemed more important to have Maxwell's equations be the clean ones without the 4 pi factors. The procedure of inserting 4 pi into Coulomb's law and the Biot-Savart law in order to keep them out of Maxwell's equations is called rationalizing the units. Of course, for people concerned more with applications of Coulomb's law than with Maxwell's equations, this procedure might look like a step in the wrong direction. But since Maxwell's equations are the more fundamental equations, there is logic in this convention. It is easy to see why the presence of 4 pi factors in Coulomb's law and the Biot-Savart law leads to the absence of 4 pi factors in Gauss's law and Ampere's law, which are equivalent to 2 of Maxwell's equations. Or actually 1.5, Ampere's law is supplemented with another term. In the case of Gauss's law, the absence of the 4 pi basically boils down to the area of a sphere being 4 pi r squared. See the derivation in section 110. In the case of Ampere's law, the absence of the 4 pi is a consequence of the reasoning in sections 6.3 and 6.4, which again boils down to the area of a sphere being 4 pi r squared, because equation 644 was written down by analogy with equation 630, or more directly, the 1/4 pi in the Biot-Savart law turns into a 1/2 pi in the field from an infinite straight wire. See equation 6.6, and this 2 pi is then cancelled when we take the line integral around a circle with circumference 2 pi r. If there were no factors of 4 pi in Coulomb's law or the Biot-Savart law, then there would be factors of 4 pi in Maxwell's equations. This is exactly what happens in the Gaussian system, where the curl B and div E Maxwell equations each involve 4 pi. See equation 920. Note, however, that one can easily imagine a Gaussian type system, that is one where the prefactor in Coulomb's law is dimensionless, that has factors of 4 pi in Coulomb's law and the Biot-Savart law and none in Maxwell's equations. This is the case in a variation of Gaussian units called Heaviside-Lorentz units. Appendix B, SI units of common quantities. We begin this appendix with the definition of all the derived SI units relevant to the electromagnetism, for example, the joule, ohm, etc. We then list the units of all the main quantities that appear in this book, basically anything that has earned the right to be labelled with its own letter. In SI units, the ampere is the fundamental unit involving charge. The coulomb is a derived unit being defined as 1 ampere second. However, since most people find it more natural to think in terms of charge than current, we treat the coulomb as the fundamental unit in this appendix. The ampere is then defined as 1 coulomb per second. Isn't that interesting? For each of the main quantities listed, we give the units in terms of the fundamental units. And then, which is mass, weight, m. No, m is distance, kilograms is mass, s is time, seconds, c is coulombs, and occasionally k, which is temperature. And then also in terms of other derived units in certain forms that come up often. For example, the units of electric field are kilogram meters per coulomb per square second, but they are also newtons per coulomb and volts per meter. The various derived units are as follows: Newton, joule, ampere, volt, Newton, joule, ampere, volt, farad, ohm, watt, Tesla, and Henry. The main quantities are listed by chapter. Okay. With charge Q, K in Coulomb's law. Epsilon 0, E field, force per charge, flux, phi, E field times area, charge density, lambda, sigma, and rho, potential, phi, energy per charge, dipole moment, is it P or rho? I'm not sure. Capacitance charge, current I, charge per time, current density J, current per area, conductivity sigma, density, current density per field, resistivity rho, field per current density, resistance R, voltage per current, power P, energy per time, speed of light is C, meters per second. B, field, force per charge, velocity, vector potential A, surface current density, current per length, electromotive force, flux phi. So the potential is lowercase phi and the flux is uppercase phi. Interesting. Inductance M and L, frequency omega. I think that's okay. It's angular frequency. Hertz. Yeah, okay. Quality factor Q is dimensionless. Phase is dimensionless. Admittance, current per voltage. Impedance. I really don't get my head around dimensionless numbers. I don't really understand. Power density S, power per area. Chapter 10, dielectric constant K, kappa. Dipole moment, torque. Atomic polarizability, polarization density P, electric susceptibility chi E, permittivity epsilon, displacement vector D, temperature T, Boltzmann constant K, magnetic moment M, angular momentum L, Planck's constant H, magnetization M per volume, magnetic susceptibility chi M, H field, permeability mu. Permeability and permittivity. Unit conversions, Appendix C. In this appendix, we list and then derive the main unit conversions between SI and Gaussian systems. As you will see below, many of the conversions involve simple plug and chug calculations involving conversions that are already known. However, a few of them, charge, B field, H field, require a little more thought because the relevant quantities have different definitions in the two systems. Conversions. Except for the first 5 non-electrical conversions below, we technically shouldn't be using equal signs because they suggest that the units in the two systems are actually the same, up to a numerical factor. This is not the case. All of the electrical relations involve charge in one way or another, and a Coulomb cannot be represented in terms of an ESU. This is a consequence of the fact that the ESU is defined in terms of the other Gaussian units. See Appendix A for a discussion of how the Coulomb and ESU differ. The proper way to express, say, the 6th relation below is 1 Coulomb is equivalent to 3 times 10 to the power of 9 ESU. But we'll generally use the equality sign and you'll know what we mean. The 3 in the following relation stands for 2.998 that appears in the speed of light, which is 2.998 times 10 to the power of 8 meters per second. The Coulomb ESU discussion below explains how this arises. Okay, we got time, the same length, scale of 10 to 100, mass is grams, force, 1 Newton, 10 to the 5 dyne, energy, charge, Coulomb, okay, potential, derivations, okay, and then we're going to go through the mathematics to arrive at these. which isn't really a good use of our time. SI and Gaussian formulas. The following pages provide a list of all the main results in this book in both SI and Gaussian units. Alright, well I don't think we care about Gaussian units, so we can skip this. Kind of cool though. Oh wow, look at all this. That's pretty heavy duty, isn't it? Wow. Yeah, wow. Insane. Alright. Appendix E. Exact relations among SI and Gaussian units. Oh, well, I don't think we're really interested in that. Curvilinear coordinates. That sounds interesting. But it uses this notation I don't understand. We begin this appendix by listing the main vector operators, gradient, divergent, curl, Laplacian, in Cartesian, cylindrical, and spherical coordinates. We then talk a little about each operator, define things, derive a few results, give some examples, etc. You will note that some of the expressions below are rather scary looking. However, you won't have to use their full forms in this book. In the applications that come up, invariably only one or two of the terms in the expressions are non-zero. Yeah, right. So this is vector operators with Cartesian coordinates, cylindrical coordinates, and spherical coordinates. Then we've got gradient, Cartesian gradient, spherical gradient, divergence, cylindrical divergence, and then another method for cylindrical divergence, curl. The curl produces a vector from a vector. The curl of a vector function was defined in 280 as the net circulation around a given small area divided by the area. The three possible orientations of the area yield the three components. In section 216, we derived the form of the curl in Cartesian coordinates, and it turned out to be the cross product of this operator, which I don't know, the upside down delta. Blah, blah, blah. Okay. The Laplacian produces a scalar from a scalar. The Laplacian of a function f, written as this upside down confounding symbol, if you know what it is, please do let me know, is defined as the divergent of the gradient. I suppose you should look it up. I'll be back. Alright, so it's called the nabla, which is the del operator. And it's got something to do with vector differential operator. So yeah, I've got a lot to learn about that. Anyway, it's called the nabla, and it is an upside down delta. Cylindrical Laplacian, and then some exercises. Exercises in the appendix, very good. Okay, let's read this. It's a short review of special relativity. Foundations of relativity. We assume that the reader has already been introduced to special relativity. Here we shall review the principal ideas and formulas that are used in the text beginning in chapter 5. Most essential is the concept of an inertial frame of reference for space-time events and the transformation of the coordinates of an event from one inertial frame to another. A frame of reference is a coordinate system laid out with measuring rods and provided with clocks. Clocks are everywhere. When something happens at a certain place, the time of its occurrence is read from a clock that was at and stays at that place. That is, time is measured by a local clock that is stationary in the frame. The clocks belonging to the frame are all synchronized. One way to approach this, not the only way, was described by Einstein in his great paper of 1905. Light signals are used. From a point A at time ta, a short pulse of light is sent out towards a remote point B. It arrives at B at the time tb, as read on a clock at B, and is immediately reflected back toward A, where it arrives at t prime A. If tb equals ta plus t prime A divided by 2, the clocks at A and B are synchronized. If not, one of them requires adjustment. In this way, all clocks in the frame can be synchronized. Note that the job of observers in this procedure is merely to record local clock readings for subsequent comparison. An event is located in space and time by its coordinates x, y, z, and t in some chosen frame of reference. The event might be the passage of a particle at time t1 through the space point x1, y1, z1. The history of the particle's motion is a sequence of such events. Suppose the sequence has the special property that x equals vxt, y equals vyt, and z equals vzt at every time t, with vx, vy, and vz constant. That describes motion in a straight line at constant speed with respect to this frame. An inertial frame of reference is a frame in which an isolated body, free from external influences, moves in this way. An inertial frame, in other words, is one in which Newton's first law is obeyed. Behind all of this, including the synchronization of clocks, are two assumptions about empty space. It is homogeneous, that is, all locations in space are equivalent, and it is isotropic, that is, all directions in space are equivalent. Two frames, let us call them f and f prime, can differ in several ways. One can simply be displaced with respect to the other, the origin of coordinates in f prime being fixed at a point in f that is not at the f coordinate origin, or the axes in f prime might not be parallel to the axes in f. As for the timing of events, if f and f prime are not moving with respect to one another, a clock stationary in f is stationary also in f prime. In that case, we can set all f prime clocks to agree with the f clocks and then ignore the distinction. Differences in frame location and frame orientation only have no interesting consequences if space is homogeneous and isotropic. Right. Now that the origin of frame F is moving relative to the origin of frame F, that's F prime, suppose now that the origin of frame F prime is moving relative to the origin of frame F. The description of a sequence of events by coordinate values and clock times in F can differ from the description of the same events by space coordinate values in F prime and times measured by clocks in F prime. How must the two descriptions be related? In answering that, we shall be concerned only with the case in which F is an inertial frame of reference. F prime is a frame that is moving relative to F at constant velocity and without rotating. In that case, F prime is also an inertial frame. Special relativity is based on the postulate that physical phenomena observed in different inertial frames of reference appear to obey exactly the same laws. In that respect, one frame is as good as another. No frame is unique. If true, this relativity postulate is enough to determine the way a system of events in one frame is related to the description in a different frame of the same events. In that relation, there appears a universal speed, the same in all frames, whose value must be found by experiment. Sometimes added as a second postulate is the statement that a measurement of the velocity of light in any frame of reference gives the same result whether the light source is stationary in that frame or not. One may regard this as a statement about the nature of light rather than an independent postulate. It asserts that electromagnetic waves in fact travel with the limiting speed implied by the relativity postulate. The deductions from the relativity postulate, expressed in the formulas of special relativity, have been precisely verified by countless experiments. Nothing in physics rests on a firmer foundation. Lorentz transformations. Consider two events, A and B, observed in an inertial frame F. Observed in this usage is short for whose space-time coordinates are determined with the measuring rods and clocks of frame F. Remember that our observers are equipped merely with pencil and paper, and we must post an observer at the location of every event. The placement of one event from the other is given by the four numbers. Okay, it's the difference between the 4 points in spacetime. The same two events could have been located by giving their coordinates in some other frame, f prime. Suppose f prime is moving with respect to f in the manner indicated in figure G1. The spatial axes of f prime remain parallel to those in f, while, as seen from f, the frame f prime moves with speed v in the positive x direction. This is a special case, obviously, but it contains most of the interesting physics. Event A, as observed in f prime, occurred at x prime A, y prime A, z prime A, and t prime A. The last of these numbers being the reading of a clock belonging to, that is, stationary in, f prime. The spacetime displacement, or interval, between events A and B in f prime is not the same as in f. Its components are related to those in f by the Lorentz transformations. Okay, x prime b minus x prime a equals gamma xb minus xa times beta gamma times c. Wow, okay. So we moved in x, so that's got more complicated. These are just the same because we didn't move in that degree, those degrees of freedom. But the time was affected. The time was affected. In these equations, c is the speed of light, beta equals v on c, and gamma equals 1 on the square root of b minus beta squared. The inverse transformation has a similar appearance as it should if no frame is unique. It can be obtained from equation G2 simply by exchanging primed and unprimed symbols and reversing the sign of beta, as you can verify by explicitly solving for the quantities xb minus xa and tb minus ta. Two events A and B are simultaneous in F if tb minus ta equals 0, but that does not make t prime b minus t prime a equals 0 unless xb equals xa. Thus, events that are simultaneous in one inertial frame may not be so in another. Do not confuse this fundamental relativity of simultaneity with the obvious fact that an observer not equally distant from two simultaneous explosions will receive light flashes from them at different times. The times t prime a and t prime b are recorded by local clocks at each event, clocks stationed in f prime that have previously been perfectly synchronized. Consider a rod stationary in f prime that is parallel to the x prime axis and extends from x prime a to x prime b. Its length in f prime is just x prime b minus x prime a. The rod's length as measured in frame f is the distance xb minus xa between 2 points in the frame f that its ends pass simultaneously according to clocks in f. For these two events, then, tb minus ta equals 0. With this condition, the first of the Lorentz transformation equations above gives us at once this expression. This is the famous Lorentz contraction. Loosely stated, lengths between fixed points in f prime, if parallel to the relative velocity of the frames, are judged by observers in f to be shorter by a factor of 1 on gamma. I'm pretty sure that's gamma. Gamma? Yeah, lowercase gamma. This statement remains true if f prime and f are interchanged. Lengths perpendicular to the relative velocity measure the same in the two frames. Figure G1. Two frames moving with relative speed v. The E is stationary in frame F. The L is stationary in frame F prime. In this example, beta equals V on C equals 0.866. Gamma equals 2. A, where everything was, as determined by observers in F, at a particular instant of time t, according to clocks in F. B, where everything was, as determined by observers in F prime, at a particular instant of time t prime, according to clocks in F prime. Question. Suppose the clocks in the two frames happen to be set so that the left edge of the E touch the left edge of the L at t equals 0, according to a clock in F, and at t prime equals 0, according to a clock in F prime. Let the distances be in feet and take C as 1 foot per nanosecond. What is the reading T of all the F clocks in A? Okay, the answer, and also, what is the reading T prime of all the F prime clocks in B? Answer, T equals 4.62 nanoseconds, and T prime equals 4.04 nanoseconds. If you don't agree, study the example again. I am not going to think that hard about it. Consider one of the clocks in F prime. It is moving with speed v through the frame F. Let us record as t prime A its reading as it passes one of our local clocks in F. The local clock reads at that moment TA. Later, this moving clock passes another F clock. At that event, the local F clock reads TB, and the reading of the moving clock is recorded as T prime B. The two events are separated in the F frame by a distance of xb minus xa equals v outside of tb minus va. Substituting this into the fourth equation of the Lorentz transformation, we obtain this expression. According to the moving clock, less time has elapsed between the two events than is indicated by the stationary clocks in F. This is the time dilation and figures in the twin paradox. It has been verified in many experiments, including one in which an atomic clock was flown around the world. Remembering that moving clocks run slow by a factor of 1 on gamma, and that moving graph paper is shortened parallel to its motion by the factor of 1 on gamma, you can often figure out the consequences of a Lorentz transformation without writing out the equations. This behavior, it must be emphasized, is not a peculiar physical property of our clocks and paper, but is intrinsic in space and time measurements under the relativity postulate. Velocity addition. The formula for the addition of velocities, which we use in chapter 5, is easily derived from the Lorentz transformation equations. Suppose an object is moving in the positive x direction in frame F with velocity ux. What is its velocity in the frame F prime? To simplify matters, let the moving object pass the origin at t equals 0. Then its position in F at any time t is simply x equals uxt. To simplify further, let the space and time origins of F and F prime coincide. Then the first and last of the Lorentz transformation equations become these. By substituting uxt for x on the right side of the equation and dividing by the first by the second, we get this. On the left, we have the velocity of the object in frame F prime, frame U prime X. The formula is usually written with V instead of beta C, as given here. By solving equation G7 for Ux, you can verify that the inverse is given, and that in no case will these relations lead to a velocity, either Ux or U prime X, larger than C. As with the inverse Lorentz transformation, you can also obtain equation G8 from equation G7 simply by exchanging primed and unprimed symbols and reversing the sign of V. A velocity component perpendicular to the V, the relative velocity of the frames transform differently, of course. Analogous to equation G5, the second and last of the Lorentz transformation equations are these. If we have x equals uxt and y equals uyt in frame F, in general the object can be moving diagonally, then we can substitute these into equation G9 and divide the first equation by the second to obtain this. In the special case where ux equals 0, which means that the velocity points in the y direction in frame F, we have u prime y equals uy on gamma. That is, the y speed is slower in the frame F where the object is flying by diagonally. In the special case where ux equals v, which means that the object travels along with the frame, for F prime frame as far as the x direction is concerned, then you can show that equation G10 reduces to u prime y equals gamma, uy goes to uy equals u prime y on gamma. This makes sense. The object has u prime x equals 0, so this result is analogous to the preceding u prime y equals uy on gamma result for the ux equals 0 case. In effect, we have simply switched the primed and unprimed labels. These special cases can also be derived directly from time dilation. Energy, momentum, and force. A dynamical consequence of special relativity can be stated as follows. Consider a particle moving with velocity u in an inertial frame F. We find that energy and momentum are conserved in the interactions of this particle with others if we attribute to the particle a momentum and an energy given as these, where m0 is a constant characteristic of that particle. We call m0 the rest mass, or just the mass of the particle. It could have been determined in a frame in which the particle is moving so slowly that Newtonian mechanics applies, for instance, by bouncing the particle against some standard mass. The factor gamma multiplying m0 is this, where u is the speed of the particle as observed in our frame F. Given p and e, the momentum and energy of a particle as observed in F, what is the momentum of that particle and its energy as observed in another frame F prime? As before, we assume F prime is moving in the positive x direction with speed v as seen from F. The transformation turns out to be this. Note that BC here is the relative velocity of the two frames, as it was in equation G2, not the particle velocity. Compare this transformation with equation G2. The resemblance would be perfect if we considered Cp instead of P in equation G12 and Ct rather than T in equation G2. A set of four quantities that transform in this way is called a four vector. The meaning of a force is rate of change of momentum. The force acting on an object is simply p to t, where p is the object's momentum in the chosen frame of reference and t is measured by clocks in that frame. To find how forces transform, consider a particle of mass m0 initially at rest in the origin in frame F, upon which a force F acts for a short time, delta t. We want to find the rate of change of momentum of dp prime dt prime observed in frame F prime. As before, we shall let F prime move in the x direction as seen from F. Consider first the effect of the force component Fx. In time delta t, Px will increase from 0 to Fx delta t, while x increases in this way, and the particle's energy increases by delta E equals Fx delta t squared on 2m0. This is the kinetic energy it acquires as observed in F. The particle's speed in F is still so slight that Newtonian mechanics applies there. Using the first of equations G12, we find the change p prime x as given by this expression, and using the fourth of equations G2 gives us this. Now both delta E and delta x are proportional to delta t squared, so when we take the limit t approaches 0, the delta t approaches 0, the last term in each of these equations will drop out, giving us this expression here as fx. Conclusion. the force component parallel to the relative frame motion has the same value in the moving frame as in the rest frame of the particle. A transverse force component behaves differently. In frame F, delta Py equals Fy delta T, but now delta P prime Y equals delta Py, and delta T prime equals gamma delta T, so we get this. A force component perpendicular to the relative frame motion observed in F prime is smaller by a factor of 1 on gamma than the value determined by observers in the rest frame of the particle. The transformation of a force form F prime to some other moving frame F double prime would be a little more complicated. We can always work it out if we have to by transferring to the rest frame of the particle and then back to the other moving frame. We could conclude our review with a remark about Lorentz invariance. If you square both sides of equation G12, remember that gamma squared minus beta squared times gamma squared equals 1, you can easily show this. Evidently, this quantity, c squared p squared minus e squared, is not changed by a Lorentz transformation. It is often called the invariant for momentum, even though it has dimensions of energy squared. It has the same value in every frame of reference, including the particle's rest frame. In the rest frame, the particle's momentum is 0 and its energy E is just mc squared. The invariant for momentum is therefore minus m0 squared c to the power 4. It follows that in any other frame, E squared equals c squared p squared plus mc to the power 4. The invariant constructed in the same way with equation G2 is given as this. Two events A and B for which this quantity is positive are said to have a space-like separation. It is always possible to find a frame in which they are simultaneous. If the invariant is negative, the events have a time-like separation. In that case, a frame exists in which they occur at different times, but at the same place. If this invariant interval is 0, the two frames can be connected by a flash of light. Radiation by an accelerated charge. A particle with charge q has been moving in a straight line at constant speed v0 for a long time. It runs into something, let us imagine, and in a short period of constant deceleration of duration tau, pretty sure that's tau, yeah, lowercase tau, the particle is brought to rest. The graph of velocity versus time in figure H1 describes its motion. What must the electric field of this particle look like after that? Figure HT shows how to derive it. We shall assume that V0 is small compared with C. Let t equals 0 be the instant that deceleration began, and let x equals 0 be the position of the particle at that instant. Okay. By the time the particle is completely stopped, it will have moved a little farther on to x equals v0 tau on 2. That distance, indicated in figure H2, is small compared with other distances that will be involved. We now examine the electric field at time t equals t greater than tau. Observers farther away from the origin than r equals ct cannot have learned that the particle was decelerated. Throughout that region I in figure H2, okay, that's the outside. The field must be that of a charge that has been moving and is still moving at constant speed v0. That field, as we have discovered in section 5.7, appears to emanate from the present position of the charge, which for an observer anywhere in region I is the point x equals v0t on the x-axis. That is where the particle would be now if it hadn't been decelerated. On the other hand, for any observer, whose distance from the origin is less than ct minus tau, that is to say, for any observer in region 2, this is region 2, the field is that of a charge at rest close to the origin, actually at x equals v2 tau on t. Right. What must the field be like in the transition region? The spherical shell of thickness ct. This is ct. Gauss's law provides the key. A field line, such as AB, there's A and there's B, I lost my place. A field line such as AB lies on a cone around the x-axis that includes a certain amount of flux from the charge Q. If CD, where's CD? Here we go, CD, makes the same angle theta with the axis, the cone on which it lies includes that same amount of flux. Because V0 is small, the relativistic compression of field lines visible in figure 515 and 519 is here negligible. Hence AB and CD must be parts of the same field line connected by a segment BC. Okay, there's BC. This tells us the direction of the field E within the shell. It is the direction of the line segment BC, which is that line in that region. This field E within the shell has both a radical component ER and a transverse component E theta. From the geometry of the figure, their ratio is easily found. Now, ER must have the same value within the shell thickness that it does in region 2 near B. Gauss's law again. Therefore, ER equals this, which equals this. And substituting this, we obtain this. But V0 on tau equals A, the magnitude of the negative acceleration, and CT equals R, so our result can be written as follows. A remarkable fact is here revealed. E theta is proportional to 1 on R, not to 1 on R squared. As time goes on and R increases, the transverse field E theta will eventually become very much stronger than ER. Accompanying this transverse, that is, perpendicular to R, electric field will be a magnetic field of strength E theta on C, perpendicular to both R and E. This is a general property of an electromagnetic wave, explained in Chapter 9. Let us calculate the energy stored in the transverse electric field above in the whole spherical shell. The energy density is given as this, the volume of the shell is this, and the average value of sine squared theta over sphere 1, okay. The total energy of the transverse electric field is therefore this. To this we must add an equal amount for the energy stored in the transverse magnetic field. Total energy in transverse electric field is this. The radius r is cancelled out. This amount of energy simply travels outward undiminished with speed c from the side of the deceleration. Since tau is the duration of the deceleration and is also the duration of the electromagnetic pulse at a distant observer measures, we can say that the power radiated during the acceleration process is this. As it is the square of the instantaneous acceleration that appears on equation H7, it doesn't matter whether A is positive or negative. Of course, it ought not to, for stopping in one inertial frame could be starting in another. Okay, speaking of different frames, P rad itself turns out to be Lorentz invariant, which is sometimes very handy. That is because P rad is energy per time, and energy transforms like time, each being the fourth component of a 4-vector as noted in Appendix G. We have here a more general result than we might have expected. Equation H7 correctly gives the instantaneous rate of radiation of energy by a charged particle moving with variable acceleration. For instance, a particle vibrating in simple harmonic motion. It appears It applies to a wide variety of radiating systems, from radio antennas to atoms and nuclei. And then Appendix I, superconductivity. The metal lead is a moderately good conductor at room temperature. Its resistivity, like that of other pure metals, varies approximately in proportion to the absolute temperature. As the lead wire is cooled to 15 Kelvin, its resistance falls to about 1/20th of its value at room temperature, and the resistance continues to decrease as the temperature is lowered further. But as the temperature 7.22 Kelvin is passed, there occurs, without forewarning, a startling change. The electrical resistance of the lead wire vanishes. So small does it become that a current flowing in a closed ring of lead wire colder than 7.22 Kelvin, a current that would ordinarily die out in much less than a microsecond, will flow for years without measurably decreasing. The phenomenon has been directly demonstrated. Other experiments indicate that such a current could persist for billions of years. One can hardly quibble with the flat statement that the resistivity is zero. Evidently, something quite different from ordinary electrical conduction occurs in lead below 722 Kelvin. We call it superconductivity. Superconductivity was discovered in 1911 by the great Dutch low-temperature experimenter Kamerlingh Ons. He believed, sorry about the pronunciation, he observed it first in mercury, for which the critical temperature is 4.16 K. Since then, hundreds of elements, alloys, and compounds have been found to become superconductors. Their individual critical temperatures range from roughly a millikelvin up to the highest yet discovered, 138 Kelvin. Curiously, among the elements that do not become superconducting are some of the best normal conductors, such as silver, copper, and alkali metals. Superconductivity is essentially a quantum mechanical phenomenon, and a rather subtle one at that. The freely flowing electric current consists of electrons in perfectly orderly motion, like the motion of an electron in an atom. This electron flow is immune to small disturbances. And, for a similar reason, a finite amount of energy would be required to make any change in the state of motion. It is something like the situation in an insulator in which all the levels in the valence band are occupied and separated by an energy gap from the higher energy levels in the conduction band. But unlike electron filling the valence band, which must in total give exactly zero net flow, the lowest energy state of the superconducting electrons can have a net electron velocity, hence current flow, in some direction. Why should such strange state become possible below a certain critical temperature? We can't explain that here, as a footnote. The abrupt emergence of a state of order at a certain critical temperature reminds us of the spontaneous alignment of electron spins that occurs in iron below its Curie temperature, mentioned in section 1111. Such cooperative phenomena always involve a large number of mutually interacting particles. A more familiar cooperative phenomena is the freezing of water, also characterized by well-defined critical temperature. It involves the interaction of the conduction electrons not only with each other, but also with the whole lattice of positive ions through which they are moving. That is why different substances can have different critical temperatures, and why some substances are expected to remain normal conductors right down to absolute zero. In the physics of superconductivity, magnetic fields are even more important than you might expect. We must state at once that the phenomena of superconductivity in no way violate Maxwell's equation. Thus, the persistent current can flow in a ring of superconducting wire. Thus, the persistent current that can flow in a ring of superconducting wire is a direct consequence of Faraday's law of induction, given that the resistance of the ring is really zero. if we start with a certain amount of flux, phi 0, is that phi? Yeah, capital Phi. Phi 0. Figure I1 outlines a simple demonstration of this and shows how a persistent current can be established in an isolated superconducting circuit. Superconductors can be divided into two types. In type 1 superconductors, the magnetic field inside the material itself, except very near the surface, is always zero. That is not a consequence of Maxwell's equations, but a property of the superconducting state, as fundamental and once as baffling a puzzle as the absence of resistance. The condition B equals 0 inside the bulk of type 1 superconductor is automatically maintained by currents flowing in a thin surface layer. In type 2 superconductors, quantized magnetic flux tubes may exist for a certain range of temperature and external magnetic field. These tubes are surrounded by vortices of current, essentially little solenoids, which allow the magnetic field to be zero in the rest of the material. Outside the flux tubes, the material is superconducting. A strong magnetic field destroys superconductivity, although type 2 superconductors generally can tolerate much larger magnetic fields than type 1. None of the superconductors known before 1957 could stand more than a few hundred Gauss. That discouraged practical applications of zero resistance conductors. One could not pass a large current through a superconducting wire because the magnetic field of the current itself would destroy the superconducting state. But then a number of type 2 superconductors were discovered that could preserve zero resistance in fields up to 10 Tesla or more. 10 Tesla is quite a lot, by the way. A widely used type 2 superconductor is an alloy of niobium and tin that has a critical temperature of 18 K and if cooled to 4 K remains superconducting in fields up to 25 Tesla. Type 2 superconducting solenoids are now common that produce steady magnetic fields of 20 Tesla without any cost in power other than that incident to their refrigeration. Uses of superconductors include magnetic resonant imaging (MRI) machines, which are based on the physics discussed in Appendix J, which is coming up, and particle accelerators. There are also good prospects for the widespread use of superconductors in large electrical machinery, maglev trains, and the long-distance transmission of electrical energy. Well, that's a bold claim. In addition to the critical magnetic field, the critical temperature is also a factor in determining the large-scale utility of a superconductor. In particular, a critical temperature higher than 77 K allows relatively cheap cooling with liquid nitrogen, as opposed to liquid helium at 4 K. Prior to 1986, the highest known critical temperature was 23 K. Then a new type of superconductor, copper oxide or cuprate, was observed with a critical temperature of 30 K. The record critical temperature was soon pushed to 138 K. These superconductors are called high-temperature superconductors. Unfortunately, although they are cheaper to cool, their utility is limited because they tend to be brittle and hence difficult to shape into wires. However, in 2008, a new family of high-temperature superconductors was discovered with iron as a common element. This family is more ductile than cuprates, but the highest known critical temperature is 55 K. The hope is that this will eventually cross the 77 K threshold. The mechanism that leads to high-temperature superconductivity is more complex than the mechanism for low-temperature superconductivity. In contrast with well-established BCS theory, named after Bardeen, Cooper, and Schrieffer, formulated in 1957, for low-temperature superconductors, a complete theory of high-temperature superconductors does not yet exist. All known high-temperature superconductors are type 2, but not all type 2 superconductors are high-temperature. Indeed, low-temperature type 2 superconductors, being both ductile and tolerant of large magnetic fields, are the ones presently used in MRI machines and other large-scale applications. At the other end of the scale, the quantum physics of superconductivity makes possible electrical measurements of unprecedented sensitivity and accuracy, including the standardization of the volt in terms of an easily measured oscillation frequency. To the physicist, superconductivity is a fascinating large-scale manifestation of quantum mechanics. We can trace the permanent magnetism of the magnet in figure I1 down to the intrinsic magnet moment of a spinning electron, a kind of supercurrent in a circuit less than 10 to the minus 10 meters in size. The ring of solder wire with the persistent current flowing in it is, in some sense, like a gigantic atom. The motion of its associated electrons, numerous as they are, marshaled into the perfectly ordered behavior of a single quantum state. Appendix J, magnetic resonance. The electron has an angular momentum of spin, J. Its magnitude is always the same, h on 4 pi, or 5.273 times 10 to the minus 35 kilogram meters squared per second. Associated with the axis of spin is a magnetic dipole moment mu of magnitude 0.9285 times 10 to the minus 22 joules per Tesla. See section 11.6. An electron is a magnetic field. An electron in a magnetic field experiences a torque tending to align the magnetic dipole in the field direction. It responds like any rapidly spinning gyroscope. Instead of lining up with the field, the spin axis precesses around the field direction. Let us see why any spinning magnet does this. In figure J1, the magnetic moment mu is shown pointing opposite to the angular momentum J, as it would for a negatively charged body like an electron. The magnetic field B, the field of some solenoid or magnet not shown, causes a torque equal to mu times B. This torque is a vector in the negative x direction at the time of our picture. Its magnitude is given by equation 1148. It is mu b sine theta. In a short time delta t, the torque adds to the angular momentum of our top a vector increment of delta j in the direction of the torque vector and of magnitude mu b sine theta delta t. The horizontal component of j in magnitude j sine theta is thereby rotated through a small angle delta psi, given by delta psi equals delta j on j sine theta equals mu b delta t on j. As this continues, the upper end of the vector j will simply move around the circle with constant angular velocity omega p. This is the rate of precession of the axis of spin. Note that it is the same for any angle of tip. Sine theta has cancelled out. For the electron, mu j has the value 1.761 times 10 to the 11 second inverse Tesla. In a field of 1 Gauss, the spin vector precesses at 1.761 10 to the 7 radians per second. That's a lot of radians per second. Or 2.80 times 10 to the 6 revolutions per second. The proton has exactly the same intrinsic spin, angular momentum as the electron, h on 4 pi, but the associated magnetic moment is smaller. That is to be expected since the mass of the proton is 1,836 times the mass of the electron, as in the case of orbital angular momentum. See equation 1129. The magnetic moment of an elementary particle with spin ought to be inversely proportional to its mass, other things being equal. Actually, the proton's magnetic moment is 1.411 times 10 to the minus 26 joules per Tesla, only about 660 times smaller than the electron moment, which shows that the proton is in some way a composite particle. If a field of 1 Gauss, oh, that's an interesting claim, isn't it? In a field of 1 Gauss, I suppose I don't know much about how such things are constructed in the standard model. I don't know. I'm planning to learn, but I haven't done it yet. About 40% of the stable atomic nuclei have intrinsic angular momenta and associated magnetic dipole moments. We can detect the precession of magnetic dipole moments through their influence on an electric circuit. Imagine a proton in a magnetic field B with its spin axis perpendicular to the field and surrounded by a small coil of wire, as in figure J2. The precession of the proton causes some alternating flux through the coil, as would the end-over-end rotation of a little bar magnet. A voltage alternating at the precession frequency will be induced in the coil. As you might expect, the voltage thus induced by a single proton would be much too feeble to detect, but it is easy to provide more protons. 1 cubic centimeter of water contains about 7 times 10 to the 22 protons. We're concerned with the 2 hydrogen atoms in each water molecule. And all of them will precess at the same frequency. Unfortunately, they will not all be pointing in the same direction at the same instant. In fact, their spin axes and magnetic moments will be distributed so uniformly over all possible directions that their fields will very nearly cancel one another, but not quite if we introduce another step. If we apply a strong magnetic field B to water for several seconds, there will develop a slight excess of proton moments pointing in the direction of B, the direction they energetically favor. The fractional excess will be mu B on KT in the order of magnitude as in ordinary paramagnetism. It may be no more than 1 in a million, but these uncancelled moments, if they are now caused to precess in our coil, will induce an observable signal. A simple method for observing nuclear spin precession in weak fields, such as the Earth's field, is described in figure J3. Many other schemes are used to observe the spin precession of electrons and of nuclei. They generally involve a combination of a steady magnetic field and oscillating magnetic fields with frequency in the neighborhood of omega p. For electron spins, electron paramagnetic resonance, or EPR, the frequencies are typically several thousand megahertz, while for nuclear spins, nuclear magnetic resonance, or NMR, they are several tens of megahertz. The exact frequency of precession or resonance in a given applied field can be slightly shifted by magnetic interactions within a molecule. This has made NMR, in particular, useful in chemistry. The position of a proton in a complex molecule can often be deduced from the small shift in its precession frequency. Magnetic fields easily penetrate ordinary non-magnetic materials, and that includes alternating magnetic fields if their frequency or the electric conductivity of the material is not too great. A steady field of 2000 Gauss applied to the bottle of water in our example would cause any proton polarization to precess at a frequency of 8.516 times 10 to the 6 revolutions per second. The field of the precessing moments would induce a signal of 8.516 megahertz frequency in the coil outside the bottle. This applies as well to the human body, which, viewed as a dielectric, is simply an assembly of more or less watery objects. In NMR imaging, or magnetic resonant imaging, MRI, the interior of the body is mapped by means of nuclear magnetic resonance. The concentration of hydrogen atoms in a particular location is revealed by the radio frequency signal induced in an external coil by the precessing protons. The location of the source within the body can be inferred from the precise frequency of the signal if the steady field B, which determines the frequency according to equation J2, varies spatially with a known gradient. Wow. Now we're up to Appendix K, helpful formulas and facts. Sounds very helpful, doesn't it? Okay, we've got fundamental constants. I think we had that in the front, didn't we? Yeah, we did. All right. Integral table. Okay. Vector identities. Taylor series. Complex numbers. Trigonometric identities. And we're up to the references. We made it. Done. Well, I'll throw over the farewell cam and we'll wrap up.
And that's a wrap. Wow. That was a pretty long session. I don't know how long it's going to be, but we'll find out. So that gets us to the end of electricity and magnetism. I'm about ready to write up the notes for chapter 1 for this, so I've got to turn that into note form, and then I've got to get on with learning the art of electronics, which I'm kind of playing schedule chicken with at the moment. It's due on Tuesday, so hopefully I get it done by then. I might. We'll see. I have to do the experiments, but I kind of know what's coming up, so yeah, I'll probably get it done. I've also got a few other things to do for work, day job, so that's going to keep me busy. I'm going to be busy for the next week or so. But hopefully we've got a video for you on Tuesday. This particular video is going to go out on Saturday. So and we did cover this. This is the last book teardown that I needed to do to have a full set of book teardowns for the Learning the Art of Electronics references. There are 5, including the book itself. So that's good. I'll have to update the documentation for that on the ITL wiki. If you don't know about the ITL wiki, it's the wiki for this channel, this YouTube channel. You can check it out. There'll be a link in the show notes. Anyway, this video is quite long enough, so I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.